I will show you later on also some experimental results, but just as a basis for calculations, we are not going into details for experiments. So numerical methods are in our focus, and it was known for a long time now, couple of decades, that finite element method can be used not only for static calculations, but also for dynamic ones, and also for fatigue crack growth. But before Belichko and his co-workers introduced extended version of the finite element method, it was too complicated to do it. So I will focus my presentation of exactly what he introduced, and not what's now. I don't see any. Okay. Yes, I think it looks like. So it was not shared. Okay. Always troubles with online presentations. I'm not saying that XFEM is nowadays the only way to analyze and estimate fatigue crack growth. In the meantime, there were some other options as well, quite good, but I'm still considering, at least for today, this one. So I will say a few words about its finally mathematical essence. So XFEM actually uses so-called enhancement functions as a means of displaying all forms of discontinuous behavior, namely crack, of course. So it is a partly analytical solution for certain number of elements, for those that are either at the crack faces already or in front of crack. Actually, that enabled simple use of the method with, of course, some other details like dividing, that we have to, of course, to know which elements will be active during this process. So this is how we can do that in mathematical terms. And this illustrates well what I'm trying to point out. A crack is going through the mesh. And we have to treat, of course, these elements that are active in that process, but we are not adapting a mesh to a crack growth. And that was the most important improvement. And that is why we still use XFEM. And as I already emphasized, there are now also efficient methods to remesh during each crack step, but that's for somebody else to say about. Abacus was, as far as I know, the first to build in this method out of commercial softwares, of course. Also, ANSYS is frequently used. And as for the elements that are at our disposal, you can see that they are not only two-dimensional, but also three-dimensional. And my presentation today is focused on three-dimensional problems. Key point in this simulation is so-called Morpheo as a post-processing of Abacus results. Morpheo is actually in charge of calculating stress intensity factors in 3D, their distribution, and according to that, to predict crack path, and then to provide all data needed for Abacus for the next step of calculation. So let us see now two examples, and then we will certainly have a better idea what I'm talking about. The first one is about welded stringer panels, which are used in A380, and they are welded either by friction stir welding or by laser beam welding. In the case we are considering today here, it is laser beam welding. And you can see in this slide which parts of A380 are constructed using these stringer panels. Here you can see how that looks like. And also you can see a model or kind of specimen, but it's more than specimen, that we used to both test and then to numerically simulate. So there is a panel, straight one. It doesn't make much difference if it is a bit curved as in reality. And there are 4 stringers welded by laser beam welding in this case. And there is, of course, a crack. So such a model was used for experimental and then numerical investigation. Also, you can see the cross section of stringers and how they are welded. So this is more or less the same with some data that we used in numerical calculation. This is linear elastic analysis. So classical high cycle fatigue problem, Young modulus for aluminum alloy and Poisson ratio are given, and then Paris law coefficients, which are obtained experimentally. And all of data that we need is actually that. So for the numerical simulation, you can see now a model with boundary conditions, and you can see enlarged in the bottom to the right, finite element mesh, one of several that we have used. This one is the only one that had weld metal modeled as well. Other models were without it. That was just to trial and error and get the best mesh to simulate most realistically panel behavior. Now we started with kind of calibration. That means we used a plain panel with a crack, 14 millimeters, for which we had also experimental results. So you can see at the bottom to the right that numerical results provided about 169 kilocycles, thousands, whereas experimental results indicated about 189, which is difference around 11%. One of the reasons for this difference is that Abacus and Morpheo typically provide a bit probably over conservative stress intensity factors. You can see in this comparison that NASGRO, which is another software that deals with the same problem, would estimate up to 10% less values of the stress intensity factor. This is important for later comparisons. And that also explains, in a way, previous difference. Anyhow, we decided not to do anything about it because our basic concept was that numerical simulation should provide conservative results. This is common engineering approach. This is what we also use for any engineering calculation. Our analytical expressions are always conservative and most of the time over-conservative. Now we have numerical solution, which is conservative, but still not over-conservative. Here you can see a couple of nice results of showing different steps for the mesh with 1 millimeter size elements. So after 68 step, crack reached the first to the left stiffener. Then after 78, you can see that it goes up and through the stiffener. And then after 130th, it's both ways already in the next segment of a panel. And at 68, this calculation was over. We cannot always use this XFEM as we like. That is maybe important to know. We simply generate a mesh, we simulate the problem, and then we let Abacus and Orfeo do the calculations, but we still are not sure when it will stop and how good the approximations will be. So this is why we were playing with different meshes. The next two examples are for mesh with 2 millimeter size and mesh with 4 millimeter size, and you can see practically about the same, just a different number of cycles. So summarizing these results, we can see that 1 millimeter mesh, which is gray one, is far the most conservative, and all other models, finite element models, converged more or less to the same value of crack length and number of cycles. So the finest mesh is actually over conservative. If we compare these results with the experimental ones, then we can see that 290,000 cycles versus experimental data, which is 418, is not really the best that we could get out of this, but it is at least conservative, and we decided to keep it this way. There are a couple of possible explanations why this estimation is around 70% of the experimental results, but I will not go into details, at least by now. And yet the final calculation that we did was to estimate the number of cycles if we put additional welded clips, which are along the crack. And to somewhat surprisingly, this improved number of cycles just for 5%. And since this is quite complicated to make, our recommendation was not to do so. So stringers are okay, they improve a lot. As you can see here, the life, because from 169,000, it goes up to 290,000, but additional 5% increase by these welded clips, that's not recommendable. So we can also conclude here that XFEM can play a significant role because we may reduce to a minimum number of experiments, because at least if we were not quite satisfied with the results, but at least we could compare different geometries by using finite element method. Now, the second example, it is also from the aeronautics. It is about wing spare. And this is now a very small plane, not that risky structure as the previous one. So here is the spar. It is practically I-beam, but it is made. It's also aluminum alloy, and it is traditionally made by riveting. Now, one of our tasks here was not only to simulate experimental results, but also to find out how much integral structure would be better. We were sure that integral structure is better, but it was necessary to quantify it. So experimental part of this research was done on kind of improvised equipment. You can see it. Here is our spar, and the results were quite interesting and realistic. You can see here spar after 58,000 cycles. First crack appeared here, it went this way and then this way. Also, at certain point, there was additional second crack in this part of the spar. Now, numerical simulation is done on the model, which is relatively simple. It's practically a consola. And there was 1 millimeter crack introduced here at the location, which was practically in all of 10 spars that we used. So this is the crack. I will speed up a bit. This is how it grows. And then after reaching this critical point, a crack in a numerical modeling went this way, contrary to the experimental one. So on the other hand side, number of cycles was surprisingly similar, but we didn't rush into conclusion that this is fantastic simulation, because first of all, crack went different way, but anyhow, we concluded that experimental crack growth for such a structure is not really predictable. It depends on local material properties or defects. So at the end of the day, we were quite satisfied with this, and we decided to go on with a numerical simulation for the integral structure. So here we see how the integral structure looks like, and then crack growths. We assumed 2 of them because experiments showed like that. And you can see how this crack grew from different angles and different number of steps. So finally, the result is 350,000 cycles, which is about 7 times more. So integral structure is far better. And not only that, but we introduced a modified integral structure with double-decker solution, in a way, with double bottom cap of the spar. Few nice figures to show how it went all the way, and the final result, 2 million of cycles. So that is a phenomenal improvement, and by that I may conclude on time. So already discussed what is written in black, but more generally, we can definitely conclude that XFEM plays a significant role in estimating fatigue life of integral structure, and not only that, but all kinds of structures. So we are not limited by geometry or type of structure, and I will just briefly run through a couple of different examples that we also simulated. These are orthopedic plates. This is artificial implant hip. This is pressure vessel with axial crack. This is a shaft in a hydropower plant. And finally, this is surface welded simulation of crack that eventually goes through it. So thank you. And just to quote Enrico Fermi, you can read it on your own. We didn't try. Actually, this was a topic for one PhD candidate, and he did this. Afterwards, we didn't have motivation to do it, but I guess we will do it in close future. So I'm sure we can improve these results. That's for sure. Also, using traditional methods, because they are now also optimized. So now you can remesh and get this, what was impossible to do it by hand, you can do it automatically now. So we will try that. Thank you for your question. Yes. Only recently people started using XFEM in plasticity as well. We still haven't, but we have in plan. It is, of course, more realistic if we consider plasticity as well. Here it is out. This is linear elasticity. Yes. Yes, I didn't have time, but in this second example, we actually use ANSYS and its method to estimate number of cycles for initiation of the crack, and it was 7,900 versus experimental value, which was 8,500. So excellent agreement, actually. Oh. Okay. Thank you very much. So it's actually good that I forgot my accreditation today. I can put them up instead.
So now I call my co-chair for this section on the next plenary speaker, Stavros.
Of the National Technical University of Athens and Professor of Mechanics at the School for Technical Education of the Officers of the Navy Force of the Greek Army, 20 Director of Interdepartmental Biomechanics and Biomedical Physics. Of the of and members of the Is written are in
Thank you very much, Mr. President, Mr. Chairwoman. Now, first of all, I would like to, should I don't feel comfortable sitting, but if you can hear me. Okay, I apologize for this. I would like to express my sincere gratitude to the IGF committee, which made this honoring invitation to me. It was a pleasure and an honor to accept. And the reason is that not only our friendship, but the fact that IGF is an example to all national sister societies like the Greek Society of Experimental Mechanics of Materials. Now, when I accepted the invitation, I had a dilemma concerning the issue that should be presented. I had a dilemma between something that is in progress, very modern, or a review of some concepts that could be considered as closed. So I decided to present some thoughts about the stress intensity factor. And finally, I think that the choice was correct. Attending this conference yesterday, the day before yesterday, I found out that more than half of the presentations are related with this concept, which is so familiar to all of us, but there are some details that should be reconsidered. So we'll discuss a few topics about the stress intensity factor. And as you will see at the end, this topic is something like the Hydra of ancient Greek mythology. You cut a head, I mean, you solve a problem, and then you find out that there are two more heads generated, two more problems or more that should be solved. So, fracture mechanics is an adventure that started more than a century ago by the pioneering works of Kirsch, English, Griffith, and so on. However, more than a century later, I think that there are some issues that are not completely closed. And the most important is the stress intensity factor. We use this concept and we have a general overview, but there are some questions. And if you follow a discussion, a current discussion in ResearchGate with a very provoking title, are the days of the stress intensity factor numbered? Is it something that will die soon? You can read in this discussion very controversial points of view. Some of the participants consider that K is without meaning. Some participants consider that it is the very heart and the pillar of fracture mechanics. About the final answer, we can see it later. Now, according to my opinion, the most critical issues that should be reconsidered are three. Some unnatural effects that are obtained when we solve problems using linear elastic fracture mechanics in 2 dimensions, which lead to the unnatural overlapping of the cracked lips. Then there is a distance between the finite domain we have in practical applications and the infinite domain considered when we solve problems analytically using linear elastic fracture mechanics. And finally, there is a problem between what is a mathematical crack with a singular tip and whether it is close or not to what we machine in practice. In this issue, late Professor Lazarin has very important contributions, which are numbered here, some of them, with his team, and which also shaped our point of view concerning the stress intensity or concentration around cracks, which are not cracks, in fact. Now, let us start with the first issue. I'll try to be as short as possible because I think that the most important thing now is discussion after the presentation. Now, what is overlapping? What you can see here, if we solve a problem theoretically in 2 dimensions in linear elasticity, the displacement field leads to what is called overlapping of the crack lips. The upper lip, the red one, overpasses the lower lip and obtains its position. Obviously, this is not a possible case to be seen in practice. However, it is predicted clearly by theoretical solutions. And it is long ago that trying to solve this problem, starting from Barenblatt in the theoretical field, and much later by Banks-Shields and her team, who tried to avoid the problem of overlapping or contact crack lips, introducing a very sophisticated, Arcan grips for URK mode loading. Harris' team, my mentor's team, also made work in this field, and they gave a condition according to which overlapping could be avoided. Unfortunately, if we look deeper in the solution, it seems that under specific combinations of load, geometry, and material, overlapping cannot be avoided. And for their solution, after 50 degrees of crack inclination, overlapping is again a result of the theoretical analysis. Much later, in the frame of a PhD study, Dr. Markidis introduced a very simple idea, very simple as a concept, but extremely complicated concerning the mathematical formulation and solution. What is the idea? To superpose to the initial ill-posed problem of overlapping lips an auxiliary inverse mix problem, which transfers the elliptical terms of the displacement field, the terms that are responsible for the overlapping, and generate the respective contact stresses that are to be exerted in order for the lips not to be able to move one on the other. You can see here the overlapping lips. You see the red one, which is the upper lip, becomes the lower lip, and the methodology adopted to overcome this solution. In fact, the linear terms of the displacement field rotate the crack as a rigid body in a position called false crack by Harris, and then the elliptical terms of the displacement field transfer the point along the lips to their new position, which finally leads to overlapping conditions. And that is to avoid overlapping. But in this case, we have to take into account the inevitably generated contact stresses. What was the contribution of this PhD is that it was possible to calculate the contact stresses in case of an infinite domain. You can see here the expressions for the contact stresses along the lips. And what is to be emphasized is that this inversion is partial. We invert portions of the elliptic terms of the displacement field, and what these portions are depend on the specific geometrical conditions of the problem. So the factors P and delta, the portions of the elliptic displacements that are to be inversed, should be checked and discussed in each case independently. Now, just for comparison, we could consider the intact disk with a linear segment equal to the crack and crack disk. And now we can calculate the contact stresses, which in the problem of the infinite medium are constant all over the crack. You can see that the contact stresses are relatively close to the stresses that are developed in the linear segment of the uncracked. And the same is true for the rotation. We have a rotation of about 2 degrees in the cracked plate. We have a rotation of about 1.3 degrees in the intact plane. Now, this was an exercise because the solution was relatively simple, since we had an infinite domain. However, this is not the case in practical applications, and the most widely used practical application is the determination of the stress intensity factor, the fracture toughness, using the Brazilian disk. It is used quite widely all over the world in case of very brittle materials like marble, stones, concrete, because we cannot implement a direct tension test with very brittle materials. There are two standards, and there are expressions which provide kappa, but we will see that perhaps they are far away from the actual result. There are problems, for example, the basic solution by Hongros considers point loads, in fact, or loading along a predefined length, the contact length between the jaws and the disc. What is the extent of the contact, in fact, and what is finally the factor? When we started dealing with the cracked finite disk, two problems together, finite domain and cracked disk, we were very conservative. We considered initially a very short crack because we wanted to avoid interaction of the crack with the boundaries of the problem. And also, we considered a distribution, not point load, a distribution of stresses along a varying contact length. This is perhaps the innovation. We accepted, and this is the case, that while the load increases, the contact arc increases also. It is not, as was suggested by Hondros, that we load the disk at an angle of 1.5 or 2 degrees. This is a varying quantity. So with these assumptions, it was possible to solve the problem assuming that overlapping is avoided, which means that for specific configuration, you can see what happens in practice. The initial crack is rotated by the linear tensor displacement, and then the elliptic terms translate the tip to a new position. So the final tip is not the initial one as a material point. This rotation was validated experimentally. Using the DIC technique, we managed to calculate the final shape of the crack, which is not anymore linear. It is an elliptic. You can see the deformity. And also an angle of rotation, which is very close to the theoretical predictions of the infinite domain. Now you can see here the predictions for the stress intensity factor. Remember that we adopted the mathematical crack concept. So there is a stress intensity factor. Obviously, it is reasonable and it has natural meaning as long as the geometry does not lead to negative stress intensity factor mode 1. So this solution was very close to the result by Atkinson, 1982. It's very familiar to all of us. He predicted that assuming point loads, the limit is 30 degrees. Using a contact arc of 2 degrees, we found something like 29.3, which is very close. Up to this limit, the solution is acceptable from the natural point of view. Obviously, the next step was to consider contact. Under specific conditions, crack inclination, contact cannot be avoided. Overlapping can, but contact no. Avoiding overlapping, we generate contact stresses. So the target, the challenge was to calculate the contact stresses in this finite domain. I will skip, obviously, all mathematical details. It was a very difficult problem from the mathematical point of view. However, these are the results. So we have naturally accepted stress intensity factors, both K1 and K2, for the whole range of the possible crack inclinations beta. You can see here the details. And what is more interesting, we validated by the method of Postix our main assumption. What is the main assumption? What is the crack? What is the contact arc? We do not know the extent of the contact arc between the jaws and the specimen as the load increases. So we had to accept the solution of the intact disk. And we have to validate. You can see here the validation. The upper results are for the intact disk, the Postix for the intact disk, and the lower figure is for the disk with a crack. You can see that the length of the caustic is almost identical. So our assumption for short cracks is validated using the solution of the intact disk for the crack, for the contact length is sufficient. Now, something that we couldn't expect. When we calculate mode 1 stress intensity factor, we suppose that the crack is under opening mode. We have to apply tensile loads. What we do in practice? We apply compressive loads parallel to the crack, and we assume that these two configurations are identical. They are not. In case we adopt the ISRM suggestion, the fact that the curved jaws impose restraints does not permit simulation and identity of these two configurations. The difference is huge. So what we obtain by using the ISRM standard is not perhaps the actual stress intensity factor under movement. And what is left now is to consider long cracks. Adopting the ISRM standard, we do not have short cracks, especially the CCNBD, the chevron cracked notched disc. The length of the crack is not very short. Obviously, this problem cannot be solved, assuming a crack, a mathematical crack, and we consider a solution with an elliptical discontinuity, and then using the semi-axis, the minor semi-axis to 0, we can go close to crack. Again, the mathematical solution was not very easy. However, the final result is quite encouraging. You can see here the predictions for the stress intensity factors and those by Atkinson. Exclude the term in parentheses, which are the normalized factors, and which is much more complicated in our case. We accepted the actual loading condition, which is parabolic and not a point load as accepted by Atkinson. We obtained results which, to our surprise, are very close to each other, even for low cracks. You can see here an example with a crack equal to 40%. And the agreement between our solution and that of Atkinson is close enough. Only the short crack solution is far from the predictions for extreme geometry. What is left now is something that is usually ignored. If we have a disk with a crack, which is loaded not parallel, neither normal to the crack, the equilibrium conditions cannot be satisfied unless we accept a distribution of friction forces. It is not possible for the disk to be in equilibrium with a crack loaded not normally, neither parallel. This problem, in fact, what is the necessary distribution of friction forces on the disk below contact arc, couldn't be solved until Dr. Hemsley contacted us because he found in our paper, in our first paper, something that was not correct according to his opinion. Dr. Hemsley is Dr. Cooper, in fact. Perhaps you know pioneering paper around 1970 with the fracture of glass cylinders. It is a pioneering paper in the study of Brazilian disc. So the family name was Hemsley, and with his help, we could solve the problem of the friction. It is not Coulomb friction, it's not symmetric, because the friction should be zero at the axis of symmetry. It is a combination of two types of friction. The first type of friction is the traditional Coulomb friction, and the second type is a friction due to deformation. So if we want to keep overall equilibrium, we should consider the effect of friction forces as we consider it in the case of contact lips, because avoiding overlapping by inversing the elliptical terms should be used when we have also friction, that is the factor T, as I mentioned. Now, the last issue is some implications caused by the actual shape of the crack, which is not in fact a crack. We use the standards of ISRM, but as Ying-Su et al. Said, if we ignore the actual geometry of the notch and the dimensions of the crack, the result that we obtain could be erroneous. So we undertook an attempt to find the stress field in case a finite disk is loaded and the discontinuity is in the shape of a rectangular notch with rounded corners. Obviously, we ignored the actual distribution, and we found some interesting results concerning the distribution of the displacement field, which could lead to lips in contact, depending on the width, on the initial width of the notch. What was more important, however, is that all stress components remain bounded. There is not a singular field, which means that perhaps the stress intensity factor is not the proper one when we deal with problems in practice where the crack is by no means a mathematical singular crack. So we tried to plot the stress components in terms of stress concentration and not the stress intensity factor. And what was very important also is that it strongly depends on the width of the notch that we machine. And also, there are differences on the stress concentration at various points of the crack notch, of the crown of the notch. So as a next step, we tried to impose the actual load distribution, which is a parabolic distribution of pressure. The results were validated again. The field is bounded. You can see here the limit for the two cases, tension and compression parallel to the crack, which are not identical. There is a huge difference here. And skipping some details, we came again to the finite element solution. Perhaps someone wonders, since we have in the 21st century finite elements, do we need analytical solutions with so many assumptions and perhaps difficulties in validating them? The answer is yes. Any finite element model somehow must be validated. And unfortunately, experimental results are difficult to be obtained, for example, on the lips of the crack. So we need analytical solutions, at least for validating the numerical tools, which are very useful for parametric analysis, for example. Yes, of course, if we want to carry out a detailed parametrical analysis, we need finite elements. So we made an analysis of the various factors that influence the stress concentration factor. And the most disappointing one is that our solution cannot take into account the third dimension. Since we use complex potential techniques, which are 2 dimensions by default, we ignore the actual stress distribution along the thickness of the disk, which is not ignorable by no means. And then we made a thorough analytical parametrical analysis, but the details are more or less expected. And the last step was to check our numerical and analytical solution in practice with a specimen made of rock, because ISRM and ASTM standards are mainly used for brittle materials. So using the 3D DIC technique, we managed to validate the fact that we do not know a priori the point where cracks start. It can start from any one of the points of the notch, depending on the geometry, either from the center of the crown of the notch or from the tips of the crown of the notch, or it can start also from the interface between the crack, between the disc and the jaw. The most important conclusion was that when we apply the compressive force according to the standard, the distance between the lips increases very smoothly and almost linearly up to 70% of the maximum load. Then up to 95% of the load imposed, we have a change of the slope. If we insist at this point, we concluded definitely by the experimental results that after 95% of the force that we consider that the specimen fractured, we have already crack propagation. The 2 halves of the disc are kept together exclusively due to the action of the curved jaws. So it is quite possible that the load we use to calculate stress intensity factors or fracture toughness overestimates, or in fact underestimates reality. It's very dangerous. That is why during a conference organized by Professor Bertolin, we proposed that the ISRM standard should be drastically reconsidered, because the load we assume as fracture load is not the actual one. Fracture has started already well before the final crack appears. So I think that this is the adventure of my team on the field of stress intensity factors. I am sure that more questions are now done before my presentation, but the conclusion that I would insist is that there are too many things to be done, even in concepts that are considered closed. And in fact, they are not. Thank you very much.
Any questions?
On the disc or on the lips of the crack? On the lips of the crack. This is the friction between radial. Then Coulomb type friction. Friction is maximizing the strength of the actual symmetry. And this is not possible. What happens in fact is that when you load, it shrinks. And this will impose additional friction force, which will superimpose the forces to the frictional forces due to an flow. This distorts the parabolic distribution, which is zero at the place where the Coulomb friction is maximized. So it is a combination of friction due to normal pressure coefficient of friction, and friction due to distortion, shrinkage of the disc center. Thank you.
Other questions? Okay. Thank you very much.
Thank you.
again.
I would like once again to thank the for this honor, and I hope that by my it was very nice. Thank you so much. Thank you.
So now we will start with the section before the coffee break. So we have one section before the coffee break. I will be the chair of this section. I would like also to mention the two sponsors of these events, MTS and Rumo, that has strongly support IGF during the years. You will find information of about companies at the end of at the back side of this room, where you will find the people that provide you information. So thank you so much for your great support. And in the Camus street, so in Via Camus, down from the stairs, yes, down from that direction, and in front of Palatina. But yes, but you will also receive. It is at 7:30. We'll also receive an email sent by Francesco that explains to you how to reach which is the time and where is the place. So you find all the information by email. Thank you so much.
Good morning, everyone.
Presentation. Yes, it was there, but so yes, it wasn't somehow. I don't know, it was there. So IGF socket, IGF27. Session 1, progress is a system. Yeah, this is the first one. Good morning. Okay. Good morning, everybody, and let me introduce the topic of my presentation, which is there on the slide. And I think this is a good example of the structural integrity analysis of the 21st century, when we are moving, we still continue working as was presented now in the aerospace and other applications, but biomedical applications are becoming more and more important because of the transition to the personalized medicine. And I would like to show you here one of the possibilities in this way, and so just the challenges which are related to it. So, but before this, I would like to invite you to the conference, which is dedicated to the analysis of the biological and biomedical materials, which will be organized in a nice place here. So just it's slightly different from Rome. So just, but there is still time to submit your abstract. And now, without any further ado, let me go so just to the presentation. And here is the type of the engineering device, which hasn't changed much in principle from the 18th century.
The only difference probably is the change in the materials. And to get the idea about the modern challenges, let us consider that this socket, which is presented here, which is being made of just either metals or nowadays polymer-based composites, it is 5 orders of magnitudes stiffer than the soft tissue. And inside the soft tissue, there is a bone, which is also the same orders of magnitude stiffer. So we have a very short transition between these two materials, and mismatch is a very significant one. So this clearly raises quite very interesting problems on the modeling part, but today I'm focusing on the structural integrity, and I would like to demonstrate the behavior of this type of the materials. And for you to understand generally, even up to now, with all our technology, the production of the sockets is more type of the art than the science. It's a very long artisan procedure where each limb is being measured several times, and then the socket is being manually adjusted, not in the way different, so just how the sculptures are being made, but the sculpture is an internal one, clearly, and then so just people are using it. And another point to remember, generally one socket is needed on average, 1.5 to 2 years. And if you are, so just if the case is of the children pediatric sockets, they need them every 3 months. So this is a very serious problem. And clearly now we all know about the potential answer to it. It is 3D printing, because you can produce this type of the sockets if you know the geometry straightforwardly indeed. And so these are the already mentioned challenges here. And this is what we are going to demonstrate you. So just let me show you a very quick video. So I will even accelerate it. Oh, sorry. So just doesn't run. Okay. Here it is. So it's generally to demonstrate you the entire process. It would take 48 hours on a modern printer to produce one socket. And this is so just for the 15-year-old male. And so still, it is significantly better than to do this in any other way. The interesting point here is that though we have the standard, which is demonstrated here, there is not much information about this. And as you can imagine, this is not a material, this is a product. So that's why the type of the loading and conditions is very straightforward one. They are prescribed and they're related to the different stages of the gate. So this caused us to design a special test rig, because clearly when we are moving, depending on the gate, there is a change in the direction of the load, which should be reproduced in the testing device. And you can see here the types of the different conditions. The first one is the strike of the foot, and the second one is the separation of the heel from this. And this is another way, so just this is part of the model which presents here the major materials which are being used in this. Currently, there is no suggestion what type of the material should be used as a model for the limb. People are using gypsum because it's easier to produce this, but clearly the properties of the muscles are totally different from gypsum. That's why we were using, for instance, silicon. And these are the types of the results that are produced in this type of the loading. You can see here the complex shape of the socket. And as a result, you can see that after this type of the loading, there is a formation of the crack, which is going in the circumferential direction here. It is in the condition 1, which is being tested. And in the condition 2, which is shown here, so just for the black so just like presented here, we have not achieved the full fracture of this socket, though we've seen some discoloration as a sign of the arrangement of the appearance of the cracks. But the important point is that all this was obtained for the significantly higher levels of the loads that are supposed to be achieved in this. Also, so just for you to understand how it is considered, the standard foresees a 5-fold weight, which is supposed to be carried by a single socket. So just practically, it's a factor of 10, because usually, as you can assume, though, in standing, it's only your weight is divided by 2. But when so just you are going, in this case, it is so just it's supposed to be 5 times higher. These are a very short result, because I'm aware that I must finish very quickly. Short result of the simulations, which demonstrates to us that this complex type of the model, I'm shown here the socket, but we have modeled the entire system, which also incorporates all the elements of the loading device and the type how it is being applied. So it reproduces and explains the amount of the displacements and the resulting forces. In the condition 1, you can see that the displacements, maximum displacements around 5 millimeters, which is sufficient to cause the cracks at the highest level of the load. While in the condition 2, sorry for a typo, which is at the bottom, it is only roughly 1/2 of this amount. And now these are the most important results considering the experimental studies. And here you can see generally that we can have here so just the results of the simulations, which are in the blue line, which are much better reproduced in the condition 2 than in condition 1. The important part is the horizontal dashed line, which demonstrates to you the load bearing capacity of the socket, which is supposed to be performed for any device of this type. And as I've already mentioned, that all the 3D printed sockets, they have successfully met the condition 1 criteria, exceeding this level by some margin. For the condition 2, we demonstrate that effectively, even at significantly higher level of the load, the socket still continued to bear the load with any significant failure occurrence in the socket. So that's why it's clear for everybody sign that we can still continue reducing the parameters like the thickness of the socket. Also, this type of the socket in the result of the printed was already 15% lighter than the one produced with the traditional ways. And so just very quickly here, so just I wouldn't go through the conclusions. I prefer to have some questions here, and because so just all these major points were made in my presentation. Thank you very much for your attention. So generally, the situation is just going for a traditional technique. So you are making a gypsum around the limb. So this is like so just imprint of this, and then you are removing it, and then you are so it's using this as a mold, and you are adjusting it. So just and this is the artisan part. That's why I was comparing to the sculptures, because people they do know where to add, where to remove, because different parts of the limb they have different levels. So in the case of the 3D printed material, because we need to produce an STL file, we are doing this as we standardly do this. It is a 3-dimensional scan. So we are obtaining 3-dimensional geometry, and then we are, so just based on this, we are adding the material, so just of the thickness which we consider reasonable, and that's where all is being done in silica.
No, only help me to find the presentation. Okay. Yeah. No. Thank you. For moving. Yeah. Oh. Thank you very much for helping me. I would like to speak shortly about the quite large type of structures. In the name of many researchers, we have a possibility to collaborate in improvement of passive safety of bus bodyworks in a roll-over accident. This type of bus accident is the most dangerous accident, and all buses now has to fulfill the prescribed testing according the rollover. You can see picture which demonstrates the test. This is a quasi-static test, the rollover, and the main condition is that prescribed safe space for passengers must be maintained during and after the rollover perform. Rollover is possible to perform physically, or, and this is a usual way, now it's possible to perform the computer simulations. We participated on two projects I have mentioned. One was performed with a Czech company from Prague, Vision Consulting Automotive, and Czech producer of buses. The project has a name, Research and Development of Articulated Electric Bus, and we were involved in testing of the whole materials from which the new sandwich roof of the bus was constructed. The second project we are solving still, we have a very nice collaboration with another research institute in Pilsen and with the producer of Poland buses, Solaris. And the focus of this project is to develop the new structure concept of the bus construction with the addition carbon fiber layers or filling foams, and to obtain the weight reduction with still very good fatigue life and rollover resistance. I would like to speak about the first project, which we finalized last year by testing the prototype of the articulated battery bus. And I will show you not scientific data, but the methodology we used during the testing, the whole materials which were used for new sandwich roof. I'm very proud for this type of collaboration because it's very useful for academic research center to have collaboration with industry. You can see schematically profile of the sandwich roof. It was necessary to perform 5 types of tests. We tested the basic materials and aluminum profiles. We performed testing of foams, testing of adhesive. We tested the whole sandwich panels, and then we tested the large roof segment test. Please image the full lorry of the material for testing because it was a very, very big experimental program. At first, we perform base testing of basic materials. of aluminum profiles and cover sheets. You can see specimens prepared for testing and examples of measured data. All data were sent to our partners, which performed the computer simulation in the digital form, or tests were monitored by video to have a possibility to compare the results of computer simulations on level of testing specimens and later on testing the whole segment of the roof. You can see the testing the foams in the tensile pressure and shear mode. The next test where this is an example of results testing at I think almost you can see example of measured data. Here is example of testing the glues. We tested some various type of glues. You can see examples of testing and mathematical modeling of sandwich panel test on this picture. And as a final part of our investigation, the segment of the roof was tested by electrohydraulic system. We tried to model the diagonal deformation of the roof during the rollover. Our colleagues which performed the mathematical calculations give us information about the speed of deformation during the rollover. And after that was possible to perform the whole simulation with the whole vehicle and to obtain the certification from certificating authority. Beside this experiments and calculations, we perform similar tests of a front part of the vehicle to understand more roll the windshield on the resistance of the bus bodywork during the rollover. All data are now secret, but if we will be invited to present the data in more detail, I hope I will be able to obtain the agreement of the company to present these results. I would like to stop with my presentation, this overview of experiments we perform, but let me give information at two programs we have at our University of West Bohemia in Pilsen for developing the international collaboration. We are able to invite the experts from abroad in the program with the name Academic Career in Pilsen for short stay, or for long stay. We have a program experts working with Pilsen. You can ask some persons sitting here. For example, Daniel Scorza has visited our university. Teresa Morgado visited me last year. Alberto Campagnolo from University Padua started collaboration with us. Vladimir Chmelko from Bratislava is collaborating with us. 4 years ago, I invited to the Pilsen Nima Shamshay with his friend Mohsen Seifi, and this year we will perform collaboration with Suhaib Barsom from Stockholm. And last two slides. Here is a lot of persons which deals with additive manufacturing and investigation of the integrity of this type of structures. We are very active in this area, my colleagues, but our laboratory are full, but we still are able to perform collaboration in production of different test specimens for together research, because we are equipped with EOS equipment, including the in situ monitoring of the printing process. And we have in our lab or all equipment which is necessary for pre and post processing of the printed test specimen. This is my invitation, and if you want, you can ask me and I can give you more information about these two programs. Thank you for this possibility to promote our recipes. Thank you.
So, ladies and gentlemen, my name is Václavík. I'm from Research Institute from Pilsen, Czech Republic, and I would like to tell you something about fatigue behavior of hybrid beam, which is a common work of our firms in Czech Republic and also from Solaris from Poland. So I would like also say many greetings to my colleagues from Poland, which have not the possibility to go here and are online. So here is the content of my presentation, and the motivation is that new high mass equipment of buses increase the mass of buses, decrease the space and limit the available passenger capacity of the bus. And solution for this can be to use hybrid materials, so some composite profiles and nodes, sandwich structures, and so on. Our idea in this project was to use very easy solutions. So use the CFRP plates which are glued on the structure on the hollow beams, and also to fill these hollow beams with some foams. But the basic considerations are to solve this is that this CFRP plates has not be debonded during the operation of the bus, because still for long time operation of the bus, still the bus may have some accident, as for example rollover accident, and the structure must withstand this high plastic deformation, and the CFRP plates has not be debonded. We use this ferritic stainless steel, which is used also for bus structure design. Pearl-threaded CFRP plates, Sika Carbodur S512, and structure adhesives, Sika Power 1277. We have also calculated this using stress-based approach, this maximum allowable shear stress and pinning stress on the end of the CFRP plate, and for 20 megapascal allowable shear strength in the adhesive, the normal stress on the spacements or on the profiles can be only 230 megapascals, which is lower value the yield limit of the material. But when we put this plates from both sides, then the allowed limit increase to approximately the yield point of the material. During fatigue test, we observed the debonding of the CFRP plate, especially with strain gauges, and according FEM support, it was calculated that when we measure 5 millimeters strains, 10 millimeter strains from the edge of the CFRP, then when the stress or strain decreased by the factor 1.71, the CFRP plate is unbonded to 5 millimeters, and this is our criterion for then evaluating this SN curve. That 5 millimeter is sufficient debonding for the structure. Here is example of fatigue test of flat spacements. We have this CFRP plate 140 millimeter length, and we also measure the distribution of strains from the end of the CFRP, and according to this, we can make calculation. We can calculate this distribution of shear stress in the adhesive, and also the distribution of the stress of the CFRP plate. So you can see that after about 35 millimeters, the stress is stabilized. Here are evaluated SN curve. On the left side, you can see the measurement of strain gauges and also this change of stiffness. The stiffness, the change of stiffness was not so good parameter for debonding, for small debonding evaluation. Only when the debonding was in a part of centimeters, so it was possible to observe the drop of stiffness. On the right side, you can see this SN curve for steel without CFRP plates, and also these circles, foot circles, are the points which are evaluated for 5 millimeter debonding. So this SN curve for a sample with CFRP plate is a little bit shifted to the lower service lives. Another part which we are tested was the structure part of the structure of the bottom part of the bus. We have some support of FEM calculation where to put the CFRP plates. On the left side, on the bottom, you can see the test in our laboratory, and on the right bottom, there is some cracks which appears and goes under the CFRP plate, but this crack appears after a longer time than when we have the steel part without CFRP. And here is the evaluation of the fatigue test. On the left side, you can see that the bottom two lines, there is stress on the before and on the CFRP plate. So the end of the CFRP plates are not debonding, but they are forming cracks on the vertical welds, which are connected to hollow beams. And here is two SNKs. The left is without CFRP and the right is with CFRP. Here are only some examples for monitoring also and with using another techniques for monitoring. So we use ultrasound, so we measure with thermocamera. We have also digital image correlations, and also we use this distributed fiber optics sensors for measurement the stains on whole lines through the sample, which it was integrated in the adhesive. This is an example of another structure part, which was side wall from the bus, and on the right side there is the monitoring the distortions during the towing tests during 2 million cycles. So conclusions: the use of stiffened hollow profiles with CFRP plates can on several joints increase the strength of the bus structure. This results in an increase in service life and a delay in the occurrence of cracks and their propagation. The beginnings and ends of the CFRP plates must lie in areas under the debonding limit stress. These areas can be determined using FEM calculation and verified using measurements with strain gauges. In properly designed hybrid structure, the hybrid beams must not delaminate during the bus service life to be able to withstand the rollover accident. So next steps is rollover simulation, application of CFRP plates to selected beams on real bus structure, and operational stress with the bus. Thank you for your attention.
Our work regards the tentative of improving the characteristic of the gamma is the alloy with the addition of ceramic compounds and ceramic materials. We have chosen the aluminum as materials. Gamma titanium aluminum based alloys have good mechanical properties, high melting point, low density, and high specific strength and stiffness. They have also a good creep resistance until 600 degrees centigrade. There are some problems in the use of these materials that are linked to the poor machinability and the low fracture toughness at room temperature. Another problem is the oxidation behavior that above 600 degrees centigrade can be improved with the use of other elements inside the composition. These materials has been used for the realization of turbine blades, turbocharged rotors, and engine valves. Our work regards the study of the effect of the oxidation dispersion. We have selected between several tested ceramic compounds, the alumina, nanosaturated alumina. And we want to look to verify the effect and the strength of this kind of alloy. We have also evaluated the addition of different quantity of alumina in 2 volumetric percent and 5 volumetric percent. We have realized with titanium aluminium, gamma titanium aluminium modified with the addition of chromium and niobium. It's a alloy just studied in the past in our department. And we have added alumina. These are the optical micrographs of the structure, obtained structure. We can observe the black particles of alumina in a matrix, in a white phases, that is the gamma titanium aluminium alloy, and also some small grain, lamellar grains that are biphasic phases. The same analysis confirmed the data observed in the optical observation. We have carried out ADS analysis on the black particles that confirm that they are alumina. And these are high magnification macro of the lamellar phases. We have carried out also an image analysis in order to evaluate this distribution of the alumina. These are the result of the 2% alumina addition, and we observed a bimodal distribution of the alumina. A more finer particles up to 5 microns, and more bigger agglomerate particles. These are agglomeration of the nanostructured particles of the alumina, probably produced during the casting procedure. In the addition of a higher quantity of alumina produce more agglomeration of this particle, and we never observed finer particles, but only agglomerated structure above 5 microns of dimension. We have studied the mechanical properties. In the test we have selected is a 4-bending test. These are the tests carried out at 900 degrees centigrade. We can observe that the non-reinforced materials doesn't break, but start to creep during the test. The materials reinforced with alumina at this temperature breaks. This is a standard behavior that we observed also during all the test, also at the other temperature. We have observed that the yield strength increase with the addition of alumina, and is more efficient a low addition of ceramic particles than a higher addition. Probably this is linked to the agglomeration and a more finer distribution that we have observed in low alloyed alloy. The effect we have evaluated also the effect on the Young modulus, and you can observe that the alumina addition improve the Young modulus of this alloy. These are the fractographic observation of the fracture surface at 800 degrees centigrade. We observe big shrinkage cavities full of dendritic structure, and also of some grains, more regular grains. The same effect. This is a problem always observed in the realization of our sample. That the cavities is almost present inside of the materials. That is due to the production technique. In this microphase, you can observe the well-embedded alumina particles and a brittle fracture surface. This is observable also in the sample tested at 900 degrees centigrade. We can conclude that the main objective of this research is to improve the mechanical properties of the gamma titanium aluminum-based alloy. The alumina, the addition of 2% volumetric percent of alumina is more effective than a higher quantity. If the technique must be improved in order to obtain a lower degree of agglomeration. In this way, we can improve the properties of this alloy. Thank you for your attention.
Thank you very much. Alcuni più recenti. Okay, so good morning, everyone. Thanks for your kind introductions. So this is the questo? Questo. Okay, so this is the outline of my presentation. So I'm going to introduce the special problem on which I'm going to focus my presentation today. It is mainly related to some modeling issues that we might face when we have to determine the overall strength and the failure probability of composite material structures. It will be based on a parametric study which take a big benefit from a reduced model that I will briefly recall, and then I will present briefly some representative results before going to some conclusion. So as we know, when we design a component made of a composite, we might also include the microstructural details, for instance, in the design to get an optimal solution. Parameters of paramount importance for the structural safety are clearly the overall strength that they will achieve, and also the understanding of the failure mode. Unfortunately, this characteristic will also depend on the local material properties, and in turn, this will depend strongly on the production processes. Therefore, usually the problem cannot be taken from a deterministic point of view, but it requires an exploration of a wide space of the parameters. So the possible alternative solution and configuration are usually identified by means of parametric studies, which are carried out of models, and the models are usually numerical. So the specific problem I will refer to today is the case of long fiber composites, focuses on the failure mechanism in a transversal plane. So there are many, let's say, different mechanisms which may contribute. One of the most detrimental is the detaching between the matrix and the reinforcement, which is known to occur also in material which have a good chemical affinity, aluminium and alumina, just to quote what has been said today. So far, another mechanism which can be alternative or which can appear together with the former one, which is typical of metal matrices, is the formation of slip bands, usually originating from the points where we have a high stress concentration close to the interfaces again between the matrix and the particles. So this failure mechanism can be interpreted, for instance, considering the growth and coalescence of microvoids which are present in metals, especially producing the processes which are typical of composites, as we see in this X-ray picture. So this kind of phenomena find a model which has been developed some already 30 years ago by Gerson, Niederman, and Vergaard. I'm just presenting here a couple of the two of the traditional equations which govern this problem. Here on the top we see that the expression of the elastic domain, which is of von Mises type, but which also consider the effect of the porosity, here denoted by the letter F, and this effect is taken into account through the pink values Q1, Q2, Q3, which are material parameters which clearly don't have a direct mechanical interpretation. On the other hand, the evolution of the microvoids can be expressed by the second equation that you see here. Here, the parameters which play a role have a mechanical meaning because they represent the mean value of the plastic strain in the material and a statistical deviation of it. But clearly, they are quite difficult to be found in practice, and they can vary from one point to the other. In the design phase, we have also to consider usually, for instance, different geometric feature, for instance, just the volume fraction of the constituents. And last but not least, in this analysis, which concern localized effect, then imperfection also play a role. These two pictures just show the different organization of the shear bands that appear in the case that the material is perfectly arranged, which is almost never the case in practical application, or if there is some offset from the position one fiber and the other one. So to try to give an answer on what will be the overall properties of this material, we must consider a lot of parameters. Numerical analyses are very time consuming in this non-linear context with this localization. So what usually is done is just to perform a limited number of analyses for some set of parameter combinations, set aside the blue dots in these two sketches, which represent just two cross-section of the parameter space, and then to interpolate. So the result, typical results are shown, for instance, here. We can have different, for instance, fields of the residual strains of the plastic strains, which in turn are reflected by different overall characteristics, both in terms of the overall strength and in terms of the ductility of the material which result from this combination. What can be interesting in this context is rather than interpolating directly the raw data, it can be effective to represent the data, analyzing the response in terms of primary deformation modes that can be superimposed. Here, for instance, on the right of this picture, we see the first two primary deformation modes, which can be combined through coefficients. which are shown, for instance, in this slide, to reproduce the response, the numerical responses, and then they can be interpolated to get, for instance, the response in correspondence of any other point inside the domain that are going to consider in their endpoints. What is interesting of this approach is that besides the fact that clearly we have only a few numbers parameters that describe each situation, and also that we can also get off of the round of error, neglecting the ideal deformation modes, which then that we can recover from the numerical analysis. These parameters are usually very sensitive to the situations we're going to consider. Yeah, we see a second, the last example, in a situation in which we have a scattered distribution of a low percentage of reinforcement. As you can see, despite the fact that the parameter f, which represents the porosity, spans two orders of magnitudes, the difference, for instance, the plastic strength response are very similar one to the other, and also the response in terms of macroscopic stress-strain relationship are very close to some extent. Nevertheless, if also in this case we perform this analysis and we simply refer to the primary deformation modes, then the coefficients tell us that the four situations, the four corner nodes, for instance, are very well defined. So we can clearly distinguish one situation from the other, and then get, let's say, a more relevant interpretation. So to conclude, these approaches, which are based on this combination of interpolation by radial basis function with a priori reduction of the problem to orthogonal decomposition, are rather common in solid mechanics. They show to work quite well also in the case of localized phenomena, which is the case that we are going to consider. And then, as I've seen, we can just use a small set of parameters to represent a complex situation. We have a high sensitivity, and with these we can, from one side, explore parameter space of large dimensionality to get the optimal response when in the design phase. On the other hand, we can also exploit this analysis, for instance, to identify those parameters, those characteristics like the initial distribution of plastic strains that we cannot determine by direct analysis, but we need usually iterative inverse analysis. That's all. Thank you very much for your attention. Thank you very much. Thank you very much.
Can open them inside. Yes. Dove si controverso. Sì, senza copiare. Lento. Okay. Okay, good morning. It is some years that I am involved in research concerning the development and use of virtual element. And today I want to show you some application of the virtual element in the field of cohesive fracture evolution. There are several numerical methods that are used to follow the fracture. in a solid. Classical methods are based on finite element, and the finite element require a very strong remeshing. In fact, we can see here the crack tip, a very fine mesh, and during the evolution, the side of the element have to be aligned with the crack. So in order to follow the evolution of the crack, we have to remesh continuously the solid. 20 years ago, a little bit more, 23 years ago, maybe, Belichko presented a new method based on the extended finite element, which require a very minimal remeshing. We have today seen a presentation by the first speaker, where the X-frame has been adopted inside Abacus. In fact, X-frame is implemented also in commercial codes. And this technique does not change the mesh, but increase the degree of freedom in the element that are crossed by the fracture. Well, the virtual element method is really a finite element method. Is a finite element, but it has a very nice property. In fact, while in finite element we are constrained to certain shape of the element, like triangular or quadrilateral, in virtual element we are completely free, and we can choose any polygon that we want with any number of sides as we desire. So, for instance, we can introduce a 5-side element with 5 nodes. That is not possible, of course, in finite element. So the question is, can the virtual element take advantage from its flexibility to be implemented in fracture mechanics? Just an idea how the virtual element is deduced. This is an element, and the idea is that we have an approximation of displacement field inside. But this approximation field is not explicitly given. We don't explicitly give the displacement inside the element. On the contrary, we explicitly give the displacement field on the boundary of the element. And if we assume that on the boundary the displacement field is piecewise linear, we implicitly can assume that inside the strain is constant and the stress is also constant. As we have not explicit displacement field inside the element, we cannot compute the gradient, the differential, and so the strain is not directly computable. The strain is indeed evaluated by a projection operator, and so that finally the stiffness matrix is computed through this, the energy associated to this projected strain plus a stabilization term. Of course, if somebody can be interested in how the virtual element is deduced, I'm very happy to discuss with him. Well, because of the specific feature of the virtual element, we, for instance, can introduce an element made by 4 sides and 12 edges and 12 nodes, of course. And we can adopt this kind of element to follow, for instance, the fracture. In fact, we can assume, for instance, that there is a crack inside this element, and we can split this element in 2 slave elements. And if the crack goes from one side to the opposite side, we have this situation. On the contrary, if we have that the crack goes from one side to the adjacent side, we have this situation. As we can see, in both cases, the situation is not standard for finite element, but can be done. This can be done for virtual element. In fact, in this case, we have 2 quadrilateral 6-node elements. And in the second case, we have a 9-node pentagonal element and a triangular element. That is not possible for finite element, but is possible for virtual element. So let's see how to apply this possibility for the nucleation and growth of a fracture inside the solid, a 2D solid. Of course, this is just a model. We computed the principal leverage strain in each element. We select the element where the principal leverage strain is maximum, and when the maximum principal leverage stress is equal to the strength of the material, and we nucleate the crack, introducing a fracture inside the element in the direction orthogonal to the maximum principal stress. In such a case, we have that this element is split in two, for instance, 6-node element, and we introduce inside the crack a cohesive interface in order to have a cohesive crack propagation. For the interface, we use the very standard model that is trilinear and accounts for the mixity of the modes. And inside this interface, we can have, of course, a part that is closed, a part where there is a process zone, and a part where there is an open crack. When we have finally this crack, we can follow the evolution of this crack, computing at this crack tip the non-local stress, and computing again on this local stress, non-local stress, the principal direction, and introducing again a new crack in the adjacent element according to the same technique. Well, just two applications. This is a L-shaped structural element that is loaded by this force. And this is the result in terms of force, vertical force displacement of this point in comparison with experimental result and with other numerical result. And we can say that the green line, that is our result, is a very good agreement with the all other result. And here we can see also our fracture line, that is the blue, is inside the cone of the fracture, the cone of the fracture that have been experimentally determined. Second test is a 4-point bending test, the initial defect, that is this one, you cannot see. And here the result in terms of the crack path and in terms of the response force versus displacement F1. And here we can see that the red circle are the experimental one, the blue circle are our numerical result, and the black star are the numerical result obtained by Belichko and Moyes with the XFEM. Well, I go directly to the conclusion, and the conclusion, the main conclusion is just in this sentence. This technique is a really minimal remeshing. In fact, there is no 1 degree increase or degree of freedom. There is just a splitting of the element without increasing increasing the problem in terms of unknown of the problem itself. Well, that's all. Sorry, very fast, but I hope you can understand the spirit of this presentation.
So thanks again for joining us in this session. Start our
Maybe during the lunch break. Okay.
Computer direct. No, this is the computer use presentation.
Bello, sono vicino a caricare. Qui, poi,
Non ti preoccupare.
no, perché c'è un filino, ma un filino in ritardo. It's fine? Okay. Ah, okay, okay. You have to change the password.
You can't see it. It's we need the PPF, the PDF.
Super. Our mind is okay. We can check it if you want. No. This session. Section 2, perfect. You are. Okay. The fourth. Maybe this one. This one.
Yes, the fourth.
Okay. Section. Okay. Obviously. First one. Oh, they place me at the first session, so I can choose. Here. You're welcome. Okay. Which is your section? Is one or next one? Is one?
Yeah.
Ninth. Is this one? No.
Yep.
Okay. You're welcome. Ah, aperto 2 volte.
Ah.
Okay. Grazie. Ok. Ah, poi. Ti chiedo, quindi una è questa? No. Oh, scusa, ok. Quindi con quale parto? Sorry. Ok. Allora. Di tu sei del sito. Abbiamo in ordine e poi questo qua va all'ottavo posto.
Dobbiamo presentare da qui.
No, però aspetta che non me la prendo.
Va bene.
Perché altrimenti chi è in remoto non so cosa fanno, vanno in risonanza, non si sa. Ok, questo è a posto, via. Piacere. Piacere, Daniela. Ok. Anche alla traccia?
Che era qua.
Cioè, poi
E la 5 che è
Posso? Yes, what is one?
yes.
And
You know how you want to upload it?
During the next session? Yes,
You
perfect.
are the speaker. You are the speaker. Perfect. Do you have the flash drive the USB panel?
Okay.
You have something to share. Okay. No worries. Yes, vuoi caricare la presentazione? Ma certo. Prego. Dai, aspetta.
non so se ero
Sei
scritto.
Aspetta che il mouse va. Sì. Allora. IGF27, perfetto. E cosa preferisci?
Se PowerPoint punti o PowerPoint.
Lo proviamo.
Sai che delle volte i simboli...
Sì, purtroppo è un problema ben noto. Sì. Allora, aspetta, proviamola così vediamo se si vede tutto. Allora, due volte la cartolina. Aspetta, qui? Ah, no. Sì, tanto ci mancano 10 minuti. Eh sì, lo diciamo. Ok. Non lo so neanche di che.
Thank you for the kind introduction, ladies and gentlemen. Good morning. I'm Daniela Scorza from the University of Parma, and the research work that I'm going to present deals with the investigation of the fracture behavior of both edge and transversally cracked nanobeams under static bending loading by using the stress-driven local theory of elasticity in conjunction with the fracture mechanics concepts. As is well known, at nanoscale level, materials show behaviors significantly different from those exhibited at macroscale level, manifesting the so-called small-scale effect. To capture such a scale effect, the stress-driven local model assumes that the strain at a given point of a body depends on the stress field of the whole body. In the case of a flexible nanobeam under a generic bending moment M, the sixth-order differential constitutive law in terms of the transversal displacement V is here written, being LC the characteristic length related to the material microstructure properties, and C the material local elastic compliance. By solving such an equation, 6 integration constants are obtained, which can be determined by imposing the constitutive boundary condition here written and 4 kinematic static boundary conditions. Let us consider the problem of the edge-cracked nanobeam shown in the figure on the right-hand side. Similar to a macroscale model, the crack is assumed as a double cantilever nanobeam. The transversal displacement V, whose expression is here shown, is computed by solving the equation of the previous slide and by imposing the 2 kinematic and 2 static boundary conditions here presented, in addition to the 2 constitutive ones. Then, the crack mouth opening displacement is determined by computing the displacement at the nanobeam end. The total strain energy stored in the deformed nanobeams may be computed as the work done by the 2 external forces F according to the Castigliano theorem. Then the energy release rate is determined and the stress intensity factor computed by exploiting the relationship with the energy release rate under, for instance, plane stress assumption. By plotting the stress intensity factor normalized with respect to the classical solution against the dimensionless characteristic length, which is defined as the ratio between the material characteristic length and the crack length L, it can be observed that when the crack is very long with respect to LC, that is lambda tends to 0, the nanobeam behaves as a large scale beam. On the contrary, when the crack length is of the same order of magnitude of LC, lambda tends to 1, and a decrease of about 40% can be observed. Let us now consider the problem of a nanobeam under bending containing a transversal crack of length A and orientation theta. In such a case, the SDM formulation for nanobeams with internal discontinuities needs to be recalled, and in particular, the nanobeam is split into parts subject to the bending moments M1 and M2, respectively. Then the sixth order differential equations governing the problem are here written, together with the constitutive boundary conditions and the constitutive continuity conditions. By solving the two above equations, the general integral solution depends on 12 integration constants. The transversally cracked nanocantilever subjected to a concentrated force at the free end is modeled by using a modification of the classical cracked beam theory. That is, the two beam segments are assumed to be connected through a massless elastic rotational spring located at the cracked section and characterized by a bending stiffness K. The transversal displacement V is obtained by using the formulation of the previous slide and by imposing other boundary conditions at the nanobeam ends and at the cracked cross-section. In particular, this boundary condition describes the jump in the nanobeam rotation at the cracked cross-section. Finally, the system can be solved giving a unique solution. The stiffness of the nanobeam at the cracked section is computed by exploiting the Griffith energy criterion to derive the compliance of a cracked plate under bending as a function of the energy release rate, and the linear elastic fracture mechanics to express such an energy release rate as a function of the stress intensity factor. The compliance is defined through the equation reported below, where F1 and F2 are the shape correction functions for both mode 1 and mode 2 loading, depending on the loading and the crack configuration. Finally, the stiffness is determined as the reciprocal of the compliance. Therefore, a parametric study on the effect of three parameters related to the crack configuration is performed, and in particular, we consider the relative crack depth C, the crack location ratio eta, and the crack orientation angle theta. In this slide, the dimensionless transversal displacement is plotted against the dimensionless axial coordinate for two values of the dimensionless characteristic length lambda and by varying the above mentioned parameters. In particular, it can be observed from the figures on the left-hand side that the displacement increases with the relative crack depth due to the increased beam flexibility. On the contrary, the displacement decreases by increasing both crack location ratio and crack orientation angle values, as shown in the figures in the middle and in the figures on the right-hand side, respectively. In the first case, it's due to the increased distance of the crack from the nanobeam constrained end. Whereas in the second case, it is due to the crack non-perpendicular to the beam axis. Finally, by considering the two values of lambda, it can be observed that the trends of the curves are quite similar, although the influence of the above parameters is more pronounced for lambda equal to 0.5. And now let us move to the conclusion. The fracture behavior of both edge and transversally cracked nanobeams under static bending loading has been investigated by using the stress-driven local theory of elasticity in conjunction with the fracture mechanics concepts. The nanobeam with a longitudinal crack has been modeled as a double cantilever nanobeam, and both energy release rate and stress intensity factor have been computed, observing a significant scale effect. The nanobeam with a transversal crack has been modeled by introducing a massless elastic rotational spring at the cracked section and the bending stiffness of such a spring has been computed by exploiting both the Griffith energy criterion and the linear elastic fracture mechanics. Finally, a parametric study on the influence of the crack severity, location, and orientation have been performed for the transversally cracked nanobeam. Thank you for the kind attention. Yes. Thank you. Thank you very much. Yes, the model can be extended. In particular, obviously, the nanobeam should be split in more parts than two, and also the formulation needs to be updated. And in particular, the most sensitive part is the definition of the bending stiffness, since the presence of two or more cracks produce an interaction between the defects. So the shape, the function f of the shape correction function needs to be rewritten to take into account the presence of more cracks. And usually this is done by a numerical point of view, some finite element simulation. Thank you.
Thank you for your kind introduction. Ladies and gentlemen, good morning. I am Andrea Zanichelli from the University of Parma, and the research work that I'm going to present you this morning deals with the experimental investigation of the mechanical properties in terms of both flexural and compressive strengths and the fracture toughness of mortar specimens reinforced with graphene oxide nanoplates. So my presentation consists of the following sections. After a brief introduction related to the cement-based materials reinforced with nanomaterials, I will describe the experimental campaign carried out on GO-reinforced mortar specimens, and then I will focus on the results obtained during such an experimental campaign, and finally some conclusions will be drawn. So, as is well known, the cement-based materials, that is mortar and concrete, are the most used construction materials all over the world, and this is mainly due to their low production costs and high versatility in response to design requirements. However, despite the many desirable features, the main drawbacks of such materials are related to their low crack resistance capability, that is their low fracture toughness, and to the presence of intrinsic defects. So improving the mechanical properties and reducing the size and the number of the defects may lead to increase the performance and durability of such materials. And an effective way to enhance the mechanical performance of cement-based materials is no. Questo? No. Niente, niente. Non la vedo più qua, però io. Si vede? Va bene. Okay. Well, okay, so. We were talking about, yes, additioning the nanomaterials into the cement-based matrix. And in particular, among nanomaterials, graphite or graphene-derived materials are reinforcing bidimensional nanofillers in the form of plates, and are able to improve the macroscopic properties of the cementitious materials due to their excellent physical and chemical properties. And moreover, according to the technical literature, GO nanoplates can regulate the microstructure of hydration crystals, and thus leading to increase the mechanical strength and the fracture toughness of GO reinforced cementitious composites. So, in such a context, let me describe to you the experimental campaign of the laboratory of the University of Parma. And in particular, at the top of the slide, you can see the raw materials we employ for the specimen preparation. That is the Portland cement, standard sand, a polycarboxylate superplasticizer, and graphite powder. And then the GO in aqueous solution was obtained the oxidation of graphite powder by employing the method. Then in the tables, you can see the mixture proportions listed by weight, and which were chosen according to the UNI-EN 196 recommendation. So note that also plain mortar space, and after 28 days of curing, both flexural compression and fracture tests were performed on both plain mortar spacements and mortar spacements reinforced with GO nanoplates. So, firstly, prismatic specimens with the nominal geometrical sizes reported at the top of the slide have been subjected to 3-point bending tests in order to determine the flexural strength RF, function of the peak load PF. And such tests have been carried out under load control until the final failure of the specimen. Subsequently, the halves prismatic specimens resulting after performing the flex test have been subjected to compression tests in order to determine the compressive strength as a function of course, of the peak load. Then, also prismatic specimens with the nominal geometrical sizing reported here and with a notch in the lower part of the section have been subjected to 3-point bending tests in order to determine the elastic modulus and the fracture toughness by means of the modified two-parameter model. And simply proposed by workers allows us to take into account the possible crack deflection during the stable crack propagation, even in case of a remote mode 1, pure mode 1 loading. And in particular, according to such a model, each specimen, as you can see in the figure on the bottom right side of the slide, is loaded the crack mount opening displacement control up to the peak load Vmax. And then when such a load is achieved, the post-peak stage follows, and when the load is equal to about 95% of the peak load, the specimen is fully unloaded in order to determine. And finally, the specimen is reloaded. So then the elastic modulus and the fracture toughness can be determined by employing the modified parameter model through the experimental ranges of the peak load and of both the initial and unloading. So here we have the results of both flexural and compression tests, and in particular the mean values and the standard deviations of both peak loads and the flexural and compressive strength for plain mortar specimens, PM, and GO reinforced specimens. And as you can see, a slight increase have been obtained in terms of flexural and compressive strength with an increment of about 4% and 3% respectively when GO nanoplates are added to the cement-based composites. And such differences may also be related to the aleatory variability and measurement errors in the container. But then Moreover, relatively to the fracture test, here I have reported one load crack mouth opening displacement curve for each specimen type. And on the right side, the peak load, elastic modulus, and the fracture toughness are listed for both plain mortar specimen and geo nanoplates reinforced mortar specimens. And as you can see, we have obtained an increment in terms of peak load when the geo nanoplates are added to the cement-based composite, whereas the elastic modulus is almost constant. And moreover, a significant increase of about 26% in terms of mean value of the fracture toughness for geo nanoplates reinforced specimens with respect to pneumonia. And now let us move to the conclusions. So in the present work, both mechanical and fracture behavior of a cement-based material reinforced with geo nanoplates have been experimentally investigated. And in particular, 3-point bending tests have been carried out on both unnotched and notched prismatic specimens, as well as compression tests, in order to determine the flexural and the compressive strength and the fracture toughness of both plain mortar specimens and specimens reinforced with geo nanoplates. It can be highlighted that the addition of geo nanoplates is able to slightly improve the mechanical properties of the present cement-based material and to significantly increase the mortar resistance to fracture. So as future developments, we have in mind to investigate different percentages of geo reinforcement, as well as the influence of geo nanoplate on the hydration process at different curing times. So thank you for your kind attention. Yeah, sure. Thank you. Yeah, okay, we analyzed our specimens with XR diffraction and SEM analysis, but what we found was that the hydration crystals were, we found the same hydration crystals actually in both the type of specimens that are the typical hydration products in the cement hydration process. Even if in the case of geo reinforced specimens, we observed with the same images that the shape of such crystal is more compacted and they are more distributed in a orderly manner in the surface. This is the influence that we observed, and we are planning to investigate more deeply these aspects in the future experimental campaigns. Thank you again.
Esatto. Adesso non l'avevo, qua non ho schiacciato questo. Sorry, condiviso, vediamo se l'ha preso il giusto. No, ah sì, adesso sì. Si vede tanto. Adesso è giusto qua. Si vede qua che da una resistance posta.
Okay, thank you for your presentation. And we study the elastic solution of a disc with a central crack. The orientation and the length of the crack are generic, and the disc is subjected to geometrical compressive pointwise loads. And this problem has been studied in many works in literature, but the most part of them are concerned only with the asymptotic analysis of the stress near the crack tips, for example, to calculate the stress intensity factor. So the elastic solution of the full field solution in analytical form is not provided in the literature. So we study the layout on the left and we can split it into system, a symmetric system which produce mode 1 condition for the crack, and a skew symmetric problem which is related to mode 2 for the crack. The system is reference is made to bipolar coordinate alpha and beta, which are linked to a Cartesian coordinate x and y, and the link of between the coordinates takes this form. And we can study owing to symmetry only one alpha of the disk. So for mode 1, the solution is the same of that of an uncracked disk, provided that the angle θ0 is lower than 60 degrees. In this case, the normal stress along the diameter is always compressive, so the cracks does not affect the solution. Vice versa, if the θ0 is greater than 60 degrees, we can have two scenarios: a partially open cracks or a completely open cracks. It depends on the length of the cracks and on the direction of the external load. But about this, I will return on the next. So the problem is a two-dimensional problem. We can study it in plane strain on plane stress. So we introduce a stress function, an area stress function key, and in bipolar coordinates we can calculate the stress field and the displacement field in this way. And we start from mode 2 condition for the crack, so for the skew symmetric problem. So we have the boundary condition on the curved boundary, and so we have to demand the shear stress to vanishing, and the normal stress sigma beta to equal the external pointwise forces. And along the diameter, we have the vanishing of the normal stress sigma beta, the vanishing of the shear stress inside the crack, and the vanishing of the radial displacement U alpha outside the crack. So we introduce the biharmonic stress function K2, and this is the most general form for the skew symmetric problem in bipolar coordinates. So this function depends on 4 functions unknown, and by imposing the boundary condition, 3 of them can be calculated as a function of, for example, F1. So we have the shear stress expression, the radial displacement expression, and just for convenience, we introduce a function U of S, and so the boundary condition led to a couple of integral equation for the function U of S. The first integral equation is the vanishing of the shear stress inside the crack, and the second integral equation is the vanishing of the radial crack outside the crack, the radial displacement outside the crack. Now, if we take for US an integral expression like cosine transform of a function of theta, it is an even function, the equation number 2 is exactly satisfied a priori. So actually we have to solve only the first integral equation. So if we put the expression of a function US in the first equation after some algebra, we arrive to an hypersingular integral equation of fifth kind. Coordinates eta and tau are just the coordinate alpha and beta rescaled, and at the bottom we see the final expression of the hypersingular integral equation. The unknown is U, and now we can, for example, we can express this function in terms of a series of Chebyshev polynomials. This allows to transform the hypersingular integral equation in a system of algebraic equation for coefficient C, and we solve it Tronic location method numerically. And once there's a coefficient C are known, we can calculate the shear stress and the radial displacement along the diameter of the disk. Just some results varying the parameter epsilon. Epsilon is the length of the crack, A over R, the radius of the disk. So small values of epsilon means short cracks. And we have on the left the distribution of the radial displacement, that is symmetric. On the right, the shear stress, and then the distribution of the displacement normal to the crack direction for a couple of angle θ0. And for mode 1, the story is almost the same. So we have to impose the boundary conditions, the curved domain, and on the diameter. But the problem is much complicated because we have to distinguish two different situations. For small cracks and high values of angle θ0, we have a completely open crack. Vice versa, for long cracks and low values of θ0, we can have only a partially open crack, so we have to distinguish two different scenarios. However, for values of angles θ0 lower than 60 degrees, the mode 1 solution is the same as that of an elastic disk, but mode 1 is still in progress. Okay, thank you for your attention. Yes. Yes, the shear stress, for example, for mode 2, the shear stress is the square root. So by simply taking the limit of the shear stress times the square root of the coordinate, they can be calculated analytically from the formulation. Okay. Okay.
Thank you, Chairman. And thanks for the introduction. So in this presentation, together with my co-authors, within this project, we have carried out some study on the fracture behavior and mechanical characterization of R350HT. R350HT is a rail steel, is a higher grade rail steel, and in general, within the rail industry, it is needed to increase the rail steel grade in order to reduce proneness to plastic deformation, wear, and crack initiation, of the crack initiation. R350HT is composition-wise very similar to the most common R260 rail steel, and but is obtained essentially by heat treatment, by basically faster cooling rates, thus reducing the interlamellar spacing in the perlite. This strengthening, so basically could potentially reduce damage tolerance, which is also a very sensitive topic in railway. Therefore, we carried out a test program on a few samples of R350HT, which is presented in this slide. And starting with the monotonic tensile test, we have extracted this tensile test according to the indications of the rail standard, of the European standard EN 13674. So the specimens were extracted from the railhead and prior to testing, some very light heat treatment was performed by maintaining the sample at 200 Celsius for 6 hours, potentially to reduce a bit of superficial residual stress and increase ductility. The tests were performed into a universal testing machine with a load capacity of 250 kilonewton by constant crosshead speed of 0.75 millimeter per minute, and the elongation was measured through an optical extensometer. Okay. Yeah, you should go to the next slide. The monotonic as a result of the monotonic tensile tests, we obtained the curves that are represented here, very let's say uniform between left and right side of the railhead, and on the fracture surface and on the remaining part of the monotonic tensile test, we have performed some investigation at the microscope. Generally, as also it's identifiable microscopically, there is a brittle fracture morphology with some, as you can see in the red frame, with some ductile area which is associated to the intergranular ferrite. As you can see, there are some dimples indicating indeed the ductile behavior. In green, you see the appearance of a radial longitudinal section, and also in this case we found some multiple cracks in this section, which were associated to the fracture of the ferrite, and close to the surface. So this is the fracture surface in the bottom. You can see the necking profile and the ductile, shear failure immediately in the vicinity of the surface, so the stress is more for plane stress, and in the immediate vicinity intergranular type of fracture. The fracture toughness tests were carried out on CT specimens, which were extracted from the railhead. Since we had UEC 54 rails, we could not extract 25 millimeter wide specimens. Therefore, we used W40 and B20 as the dimensions of the specimens, with the notch pointing downwards. The specimens were machined producing integral knife edges. Therefore, the crack compliance was measured using CT, the clip-on displacement gauge. And as a result of this test, you can see here one of the curves. Essentially, what we realized is that at room temperature, a valid K1C test was very difficult to obtain according to the American standard, although mostly because of the prerequisite of having a ratio between maximum load and PQ, let's say lower than 1.10%, but this condition was weighed somehow into the European standard. Therefore, we had a valid test according to the European standard, and according to the American standard, a valid K1SI test, a size-insensitive fracture toughness, plane strain fracture toughness. In this case, the slope of the secant that is used to calculate and identify PQ is not the 95%, but is a function of the remaining ligament, is a relatively new procedure in the standard, and therefore is related to a fixed crack extension of 0.5 millimeter instead of the 2%, which is underlying the estimation of K1C. Related to the surface, you can see in the green box, this is the crack front of the. Oh, you don't see that. This is the crack front of the pre-crack, and you can see the onset of cleavage cracking and several initiation points. Even at room temperature, there was no really ductile tearing because it's a very brittle steel, and more into the far away from the crack front of the pre-crack. You can always see, as in the tensile test, some zones which are associated with the intergranular ferrite in the yellow box, where some ductile fractures occur. Relating to the fatigue crack growth rate, I think solution is, yeah. Related to the fatigue crack growth rate tests, we have performed tests in using two load ratios, but only one is reported in this presentation for sake of time. You can see here the experimental data compared with the Paris curve from literature, and this Paris curve were mostly were actually obtained for R260. Just to make a comparison, we can say that generally the fatigue crack rate is not much higher than what you obtain in R260 rail steel. As analysis of the fracture surface, you can observe here the macroscopic appearance of the fracture surface, with this being the from left to right, the crack growth direction under constant indeed delta P. That's how we perform the test. The constant load range. On the going from left to right, we observed an increased roughness, so different higher depth of the fracture surface, and the crack growth was characterized as intergranular crack growth. So therefore, a smoother surface is obtained at the lower crack propagation rates. Going to the conclusions, monotonic tensile test properties generally are uniform within the head and generally higher than R260. Rail steel, usually the number for these rail steels identifies the Brinell hardness. The morphology of the fracture surface reveals a typical brittle fracture type with some limited necking. Multiple cracking sites were associated to intergranular ferrite. A valid K1 SI according to the STM E399 standard was obtained, and the valid K1C test result according to the European standard were obtained for the W 40 millimeter CT specimen at room temperature. A ductile behavior is locally exhibited due to the intergranular ferrite. Fatigue crack rate is similar as R260 rail steel, and increased surface roughness is observed with increasing stress intensity factor range while the crack propagates. And thank you for your attention. I reported the value. It's about 40 megapascal square root of meter, or 1,222 megapascal square root of millimeter. And it's in line with the tests that were characterizing the material at -20 Celsius. Well, in this part is not really visible, but for the fatigue crack growth rate test, we had the intergranular crack growth. So generally, also we didn't see much. Yeah, okay, I will. Yeah, yeah. Okay. Thanks.
Okay. Hello, good day, everyone. I am Shakiba Zolfagari, PhD candidate at Isfahan University of Technology, Iran. I'm very proud to present the topic fracture prevention and repair via FRP to concrete joint using externally bonded reinforcement on grooves technique under supervision of Professor Mostofi Nejad, Nicolas Pantuzzi, Raimondo Luciano, and Francesco Fabrocino in this conference. The list of contents that will be presented includes introduction, background, research objectives, experimental program, experimental results, and finally conclusions. FRP products are considered serious competitors and even alternatives to steel products due to their numerous advantages such as high strength weight ratio, low corrosion, acceptable modulus of elasticity, neutrality against electromagnetic waves. Structures need to be strengthened for various reasons, such as errors in design and execution of structures, inefficiency of old codes, destruction of materials and corrosion due to destructive environmental factors or age of structure, increase of load on building, or changes in structural members. Major strengthening technique for reinforced concrete structures are steel jacketing, concrete jacketing, FRP jacketing, externally bonded steel plates, and externally bonded FRP sheets. Despite having a higher price, FRP materials have many more advantages, such as dimensional stability, ease of installation, reduction of maintenance costs, reduction of transportation and assembly costs compared to traditional materials. For reasons such as vandalism and fire, according to ACI 440, the strengths, the existing strengths of unstrengthened structural member should be enough to resist future service load. Also, this guide limits the ambient temperature of the reinforced structures to 15 degrees Celsius, lower than the gas transition temperature of the FRP composite. Moreover, the tensile strength and compressive strength of existing concrete substrate in bond critical applications should be at least 1.4 and 17 megapascal. To strengthen reinforced concrete members through the external installation of FRP sheets on the concrete surface, EBR method and grooving method in three forms of externally bonded reinforcement on grooves or EBRAG, externally bonded reinforcement in grooves EBRIG, and externally bonded reinforcement in and on grooves EBRIOG methods have been proposed. The failure modes of RC section flexurally strengthened with FRP sheet can be FRP failure in tension and concrete crushing in a compression after or before yielding of tension steel. In general, FRP failure or failure of FRP and FRP to concrete joint can be due to FRP rupture or detachment of the sheet from the concrete surface. Debonding can be in the form of surface debonding, including FRP delamination, debonding and FRP sheet adhesive interface, adhesive debonding, debonding of concrete adhesive interface, concrete substrate debonding, or deep debonding at SL bar level. In RC beams strengthened with FRP sheet, two types of debonding in the form of IC debonding and PE debonding happen. In IC debonding, which from the point of view of failure mechanics is of the mode type 2, the stress state of the critical region of the beam is like of that block in the single lap shear test. So many studies have been conducted to determine the behavior of FRP to concrete bond based on a single lap shear test. FRP to concrete bond behavior can be defined by 4 characteristics: failure mode, maximum load capacity, that if the bonding failure happens, is equal to bond strength, effective bond length, and finally governing relationship between bond shear stress and slip. Particle image velocimetry technique can be determined can be used to determine the displacement and strain fields for having load slip curve and strain and stress profiles along the FRP bonded lengths and also bond slip curve. By conducting 154 single lap shear tests, Muqaddas and Mostofi-Nejad presented the first model for bond strength via EBRAC technique. Then they presented another model for evaluating the effective bond length and a model for bond slip relationship for EBRAC technique. In 2021, Mohammadi and Mostofi-Nejad, by bringing up the topic of groove classification, investigated different square groove classification in EBRAC FRP to concrete joints. Zamani and Mostofi-Nejad in 2022 presented a model for calculating the failure strain in EBRAC joints. In present research, our goals are investigating the effect of groove width and depth variation on the behavior of FRP to concrete bond and a better understanding of the bond behavior of the sheet to concrete surface. Determining the stress and strain details in the length of the sheet to concrete bond surface using the PIV technique, determining the optimal groove dimensions for fracture prevention and repair via FRP to concrete joint using externally binded reinforcement on groove technique, and validation the related relationships presented in the literature. In this research, one single lap shear test on an EBR specimen and 12 single lap shear tests on EBRAC specimens were considered. Grooves with widths of 2.5, 5, 10, and 15, and with the depths of 2.5, 7.5, 10, 5, and 15 millimeters were examined. Oh, okay. Two methods of EBR and EBRAC technique were used to strengthen the specimens. The failure mode for all the specimens were debonding. For EBR specimen, it was concrete substrate debonding, and for EBRAC specimen, it was concrete surface debonding out of the groove and debonding at concrete adhesive surface on the groove. If I want to summarize the conclusion in this research, according to this table, the bond strength for all the specimens are shown in this table. The EBRAC method shows 14 to 73% high bond strength rather than a specimen with EBR method. For the two specimens with the same cross-section, group cross-section, the specimen with greater width showed higher bond strength than the specimen with greater depth. Esters and estering details in lengths of sheet to concrete bond surface were obtained using a PIB technique. If I want to go to conclusions, the EBRAC specimen exhibited 14 to 73% higher bond strength compared to EBR specimen, showing the superiority of the EBRAC method over the EBR method in delaying separation. In the group depths of 5, 10, and 15 millimeter, the highest bond strength was obtained corresponding to group widths of 10, 5, and 15 millimeter respectively. The results show that the optimal group depth for group widths of 2.5, 5, 10, and 15 millimeter is equal to 5, 10, 5, and 5 millimeter respectively. Among all the groups in this study, the group with widths of 10 and depths of 5 with the highest bond strength was the optimum one. Chen and Teng's model for EBR specimen overestimate the bond strength for EBR specimen and underestimated for EBRAG specimen in this research. The model presented by Muqaddas and Mostofinejad predicted the bond strength in the overestimate for EBRAG specimen in this research. The relationship proposed by Zamani can be valid for the EBRAG specimens up to their optimum depths. This relationship doesn't consider the existence of an optimal depth for a constant width of the group, and for depths greater than the optimum depth has still an upward trend for strain. Thank you for your attention. Thank you.
Thank you, Luciano, for the presentation. Good morning to everybody, ladies and gentlemen. And the work is based, is produced on natural fiber-based composite laminates. As you know, polymer composites are used in any industrial area, given to a lot of advantages with respect to conventional material. It is the lightness of the polymer composites, but also the corrosion resistance, the versatility, high strength to weight properties, in general, high specific properties. And among these, a lot of interest is dedicated to the fiber reinforced polymer composites, because they are used in the many industrial fields as structural composites with respect to conventional ones that are based on metals or other metals. Polymer composites have some, in particular thermoplastic composites, have some advantages that goes from the toughness to the lightness to the recyclability. Intrinsic recyclability is important from an experimental point of view, but also the faster processing of these materials. But their wide diffusion is always has been limited and slowed by the high cost of tools and materials, but also by the strict know-how about design and manufacturing, but also by the low temperature for safe use with respect to thermosetting composite materials, because in this case we have a glass transition temperature that usually is lower than 100 degrees. In case of epoxy resins, you may have also, or other thermosetting polymers composites, you may also have a glass transition that goes through 150 degrees or higher again. And this advantage has been enhanced in the last years by the advent of the so-called natural fiber composites, because in this case, in particular green composites, because in this case we have bio-based materials and natural fiber materials as reinforcement that usually have a lower resistance with respect to temperature, with respect to pressure that you may use to impregnate the fibers. And in this case, you have to take also into account that there is not uniform properties of the fibers. That depends by many situations, also by the humidity. And in this case, you don't have a good adhesion interface because you have a natural hydrophilic in a matrix that usually polymer matrix is hydrophobic, so interface is not very good. And all these challenges have to be faced. So starting with these two reasons in which the use of thermoplastic composites is limited, especially in such application, given the high viscosity of the molten matrices, because you have to impregnate with the polymer first, and you have to use high temperature to lower the viscosity, or to use high pressure. But in both cases, you may damage the reinforcing fabric or the reinforcing fibers. And take into account that this effect are enhanced in case of more sensible bio-based matrix and natural fibers. In that case, it's important to note that the need to have an increase of the knowledge of the materials, but also of the process in order to gain a good effect on the finished products. And so this work is focused on composites based on bio-based matrix, that is the polylactic acid, and Utah fibers that are organized in a fabric. There is a woven fibers. And the aim is to highlight which are the challenges from the technology point of view that you have to face in order to have a finished product with the properties that are competitive with composites based on synthetic raw materials. So we are made with the typical processing approach, that is the film stacking and hot compacting with the press. We combined the polylactic acid with the Utah fiber fabric, and we tested the specimen with the weighted sides that are cut directly from the plates that we obtained with this technique to obtain specimens for tensile tests and for flexural tests. And then we compare the experimental results with the theoretical results, and we see that there's a high discrepancies between this data. So these are the experimental results, the tensile tests and flexural tests, as I said before. We processed the stress strain curves in order to obtain some parameters, but I want to focus the attention on the modulus, because we have determined this modulus also using a very simple theoretical approach. And we see that in this case, in case of tensile stress, in tensile proof, we have a Young modulus of 2.5 gigapascal. That is very similar to the tensile modulus of the matrix, while the fibers have a highest elastic modulus, and the final product not approach this value. This is due to the fact that the fibers doesn't work at the best. As I said before, we determined the elastic model using a simple theory approach. We're using these two expressions to obtain the modulus along the weft along the warp. And we know that in case of our architecture of the texture, the decay is 0.5, because we have a plane wave texture in which the number of fiber along the warp is equal to the number of fiber along the weft. So we have the same rigidity in both directions. So we have to determine K is 0.5. We set this value 0.5 given the architecture of the fabric, and we have to determine the launcher and Young's modulus by considering that which are the characteristics of the raw materials. In case of the isotropic matrix, from the technical database, we have 3.5 gigapascal, and about the fabric, we have 40 gigapascal of the fabric. So we have determined the fraction volume of the matrix and the fiber, given the nominal area weight of the fiber, given the thickness of the fabric. simply it is possible to determine which is the amount of fiber inside of my plate, and we have determined as a consequence also the amount of the matrix. Given all this parameter and set this parameter inside of the simple model that I showed before, we may obtain which is the theoretical stiffness that we have to obtain in both directions, transverse and longitudinal direction, that is 10 gigapascal. If we take into account which are the characteristics of the matrix and the fibers. And we remember that the experimental value is lower, so there is a discrepancy, but this is expected, and this is hence which is the challenge that we have to face. We have a matrix and we have fibers that have difficulty to stay together because the interface is not good, and we have to compact by hydraulic pressure the matrix in order to have a good impregnation. This is difficult because when you heat the matrix, it's not a thermoset in which you have a liquid. Now we have a viscous fluid, and the viscous fluid, if you use a high temperature, you may degrade the matrix. If you use also the fibers, if you use a high pressure for compaction, you may distort, you may deviate, which is the right texture of the texture, and you change all the kinetics of the impregnation. So we have to face this problem that you have during the development of this process. So the problem related by the percentage is that a new manufacturing process is needed, perhaps considering the physicalization of the matrix or the fibers in order to have a good quality interface, but also considering a good balance between the temperature and pressures in order to have materials that at the end, as finished product, have properties that are comparable with conventional materials. Thank you very much. Yeah. Yes, it is. It is possible to improve. You have to reduce the voids and you have to have a good interface. But to do it, you have increased the temperature, for example. But if you increase the temperature has to be so high in order to have a low viscosity of the matrix, but not so high in order to degrade the fibers and the matrix. You may increase the pressure. If you increase the pressure, you may have a good impregnation, but at the same time, you may disalign the fibers because you are considering a fabric. And in this case, the architecture of the fabric has to remain the same. If you increase the pressure, you may have a good impregnation, but not a good alignment of the fibers. You may increase the time for each step of pressure, but also in this case, you have to take into account which are the sensibility of the matrix and the fibers at high temperature. There are a lot of chances to be faced, and it is just a contribution to highlight which are the challenges in order to develop to industrial scales and natural fiber polymer composites.
Thank you, Prof, for the presentation. The research was conducted in collaboration with Professor Rosa Penna and Professor Luciano Feo and Arturo Pascuzzo. The presentation will follow the following points: introduction, state of art, material, scope and novelty, results and discussion, and finally conclusions. In recent decades, there are hundreds of applications of nanomaterials in various sectors, especially in the field of NEMS. Nanotechnology is shines engineering and technology at the nanoscale and indicates the set of techniques and methods aimed at creating a system in which at least one dimension is of the order of nanometers. As it is well known, for the study of static and dynamic response of nanobeams, it is necessary to use non-local elasticity model. Hence, the classical Cauchy local model in which the stress at a point depends only at the strain at the point cannot be used. In 2017, Romano and Barretta have been introduced the stress-driven model, which appeared well posed from a mathematical point of view and provides a stiffening, coherent approach for the study of nanostructures. The integral form is equivalent to the differential form if and only if the two pairs of constitutive boundary conditions are satisfied at the nanobeam ends, where LC indicates the characteristic length and is function of non-local parameter and in which allow you to capture the small scale effects, while M and K indicate the bending curvature and the bending moment. As the size of a structure decreases, the surface area to volume ratio increases, and the surface area region cannot be neglected. For nanometric size, the energy stored in the surface, also called the free surface energy, is significant and leads to the formation of residual surface tensions and elastic properties different from those of the bulk. The surface properties is dominant at small scales. One of the first mathematical theories incorporating surface energy was proposed by Gurtin and Murdoch in 1974. The surface of the nanobeam is modeled as a zero-thickness membrane perfectly bonded to the underlying material, and no slipping between the surface and the bulk material is admitted. Moreover, bulk continuum and surface layer are characterized by different stress states. In particular, a uniaxial stress state for the bulk, but unlike the classical Bernoulli-Euler beam theory, the component of the bulk in the transverse direction, which describes the surface layer and the bulk interaction, is not negligible due to surface effects, and is here assumed to vary cubically along the functional graded thickness of the nanobeam. While for the surface layer, the two relevant constitutive formulation are reported, where ES is the Euler-Young modulus for the surface layer, and tau S is the residual surface stress. Functionally graded materials have become of great interest in numerous research fields, as shown in this slide. But for the study of these materials, it is necessary to use a micromechanical model, such as the Dvorak model, where N indicates the material gradient index, while PC and PM are the generic physical or mechanical properties of the material listed in the table. In this work, ceramic and metal are coupled. The aim of this work was to couple the pure non-local stress-driven model with the theory of Gurtin and Murdoch for a function-graded material in the presence of a crack or low discontinuity. Combining the above theories, the governing equation incorporating surface effects, surface energy in terms of transverse displacement of each part of an inverted nanobeam can be obtained, where IE is the equivalent bending stiffness to take into account the surface effects, while TS is defined as follows. Let us assume that the function graded nanobeam has an edge crack located at a distance d from the left and which divides the nanobeam into two parts, B1 and B2, subjected to distributed loads. To take into account the effect of the crack, we use the method proposed by many authors. The crack can be modeled as an elastic spring at the cross-section between the two parts, whose flexibility constants are denoted as follows. Thus, due to the presence of an edge crack, we can evaluate an increment of strain energy with respect to an intact nanobeam. In this work, the crossover flexibility constants Kmn, Knm are assumed to be zero. Moreover, no longitudinal displacement is considered, and only the bending problem is investigated. investigated, and hence the increment of strain energy related to KMM can be expressed as follows. Consequently, the following relative boundary conditions at the crack position must be considered, where K indicate the crack severity. Thus, we have two equations. In red, the equation for the first part of the nanobeam, and in green, the equation for the second part. The above two equations, which present 12 unknown constants, must be solved with the specified boundary conditions. 4 standard boundary conditions, 4 compatible boundary conditions, 2 constitutive boundary conditions, and 2 constitutive continuity boundary conditions. In particular, we have the standard boundary conditions, but in red are highlighted the terms that take into account the surface effects. The compatible boundary conditions are the continuity of the vertical displacement, jump in bending slope, continuity of the bending moment, and continuity of the shear force. In addition, we have the constitutive boundary condition introduced by Romano et al. And the constitutive continuity boundary conditions. In particular, the constitutive continuity boundary conditions introduced by Caporale et al. in 2020 are modified to take into account the surface effects. For reason of timing, now I show you only the main results obtained for a clamped dependent functional graded nanobeam with discontinuity distributed load and the crack. In the slide, I show you the results in terms of dimensionless deflection for both SDM model with and without surface effect by varying the crack severity and for two value of non-local parameter. As it is to see, the stress-driven model that take into account the surface effects always gives a lower value than the stress-driven model without the surface effects. And by comparing the two figures, by increasing the non-local parameter, a decrease in dimensionless reflection we obtained, and by increasing the crack severity, the dimensionless reflection increase. In addition, in this slide, I show you the results in terms of dimensionless deflection for both model and for different function graded material. In this case, it was set on a local parameter equal 0.2 and the crack severity equal 0.065. In particular, as can be seen, the dimensionless deflection increases as the gradient index of a material increases. In view of the numerical results obtained in the present study, the following conclusions may be formulated. The deflection increases always by increasing the material gradient index. An increase in the value of a local parameter always leads to a decrease in the deflection for both models. The deflection always increases as the crack severity increases. And finally, the surface energy effects cannot be neglected, and for both non-local model used, the value of maximum dimensionless deflection are lower than in the case of no surface effects. Thanks for your attention. This? Yes, the spring are set with parameter. With we modify the parameter like the literature with by comparing with the others models, and we prefer to use a numerical parameter that in literature is 0, no crack, 0.065, 1, and 2.
you, Professor, for the presentation. The supervisor of this work are Professor Luciano Feo, the Professor Renzo Martinelli, the Professoressa Rosa Penna, and Marco Pepe. Well, after a brief introduction and the presentation of the material used, the kinematic assumption and the constitutive law of the cracked-hinge model are formulated. Next, the calibration of the matrix stress strain parameters and of the bond slip law for the steel fibers will be presented in order to compare the model prediction with the experimental results. First of all, the experimental results were those presented in this work by Meng and Keyant, and were here used to improve the cracked-hinge model already formulated by these authors, in which a mesomechanical approach was adopted. The aim is to predict the bending response of ultra-high performance fiber-reinforced concrete beam elements by varying the percentage of carbon nanofillers. As regards the material, 6 mixture composed of steel microfibers with a fixed content of 0.5% and carbon nanofiller with a variable content ranged from 0 to 0.3% were considered. For the model, first of all, a standard spacement transversally notched at the mid-span section was considered. The model is able to consider the bridging effect offered by the fibers, so the total number in the mid-span section can be evaluated as the ratio between the total volume of the fibers and the volume of the single fiber. Hence, a random distribution inside the spacement prismatic volume was generated by utilizing the standard random number generation in MATLAB. For the kinematic assumption, the model is inspired to so-called cracked-hinge approach. So, first of all, the flexibility was distributed only in the center part of the spacement, while a rigid body behavior is exhibited by the remaining end part. If we discretize the NC layers of the mid-span cross-section, it's possible to evaluate it as follow the average axial strain before crack formation and the crack opening displacement after crack formation. It means that the stress value, the axial stress value, can be evaluated as a function of the axial deformation before crack and a function of crack opening displacement after the crack formation. In the end, as regard the bridging effect offered by the fibers, it was taken into account by introducing the action Fk mobilized at JTH step of the incremental analysis. And it can be evaluated as the product between the fibers area and the axial stress that was correlated to the bond stresses mobilized on the lateral surface of the crack, but also to the crack opening displacement. For the constitutive law, when the concrete is in compression, its behavior is described by this relation that depend on the strain at the maximum compressive stress and on the plasticity number. The tensile behavior is described by 2 diagrams. Until the section is uncracked, a stress strain diagram should be used, while after the crack formation, a stress crack opening displacement should be used. As regards the steel fibers, the mathematical relation of the local constitutive law adapted in this study is provided in this equation, where S is equal to the crack tip opening displacement, while the other 5 parameters have to be calibrated with respect to the experimental investigation. In particular, this constitutive law is divided in 3 branches. A linear elastic behavior up to the stress level that correspond to the matrix stress tensile strength, a softening behavior characterized by the formation of micro cracks in the mixture and a constant behavior. As regards the calibration, an inverse identification procedure was carried out with the aim to determine the value of the non-local parameters that led to minimize the effect between the measured and the predicted force displacement curves. So first of all, the calibration of the fracture energy parameters is connected to by modifying only the crack opening displacement W1 through the parameters alpha, but also the initial fracture energy and initial strength, compressive strength. As regards the calibration of the bond slip law parameters, first of all 5 parameters were calibrated for spacement without nanofillers, and then only the 2 bond stresses were calibrated again for reinforced spacement, while the other parameters were considered constant. Here we can see better the initial branches of the bond slip laws. Here are reported the results. So the comparison between the numerical models represented by the colored load deflection curves and the experimental one represented by the black and gray curves. It's possible to note that the results are the curves are very match almost perfectly in the first part, and then for a content higher than 0.1%, hardening behavior is exhibited. It can be noted that the calibration of the stress strain behavior of the matrix in terms of fracture energy results in an almost linear correlation between the increase of content of nanofiller and the increase of fracture energy. At the same time, the back analysis of the bond interaction between the matrix and the steel fibers show that the increase of nanofiller dosage is linearly correlated to increment of the bond stresses. So in the end, the good agreement between the experimental data and the numerical results have been observed. However, future experimental results are needed to calibrate the general relationship between the main parameters that control the bond slip law of the fibers and the stress-strain relations in presence of nanofiller. Thank you for your attention. Well, we refer to experimental results. Anyway, several studies show that the increment in the content of nanofiller does not present an increment in compressive strength. Hence, the content, the higher content of nanofiller shortened the distance between the fibers. This led to an increment in the van der Waals force, and there is an agglomeration of nanofillers. Thank you.
And not exactly by Bernard Spischak. Good afternoon, everyone. My name is Bernadette Spischak, and I would like to say a few more words about the simulation work we have been doing in my Institute for Applied Research. It's called Simulation of Crack Propagation using the GTN ductile damage model based on the virtual crack closure technique. Before doing anything about what the simulations were done, I would like to say a few words about the background and the aim of the work. First of all, we are working with nuclear power plants, therefore it is related to this topic. There are quite a lot of reactors already operating all around the world. There are more than 400 of them, and most of them, at least half of them, are already over than 30 years old. Therefore, it is very important to have aging management in case of these reactor pressure vessels. For this, we need more information about the material properties of the equipment, and also we need some solution for this. One of them is to transfer the material properties from small scale to large scale components, and also the second one is to use miniaturized specimen. But for these results, we don't have standardized calculations which could be used. Therefore, our work is basically with the following content. First of all, we determine the GTN parameters, which is related to ductile behavior with anti-specimens, where we use artificial neutral network. Thereafter, we apply these parameters for 1T CT specimens to validate the results. Thereafter, we use the unloadings in case of the simulation. So with the standard method could be evaluated and the J delta curves could be determined. We compare them with the testing and they were showing quite good results. And finally, I will say a few words about what is the new thing about our calculation is the VCCT model, where we update it with our thoughts. So the first step is to determine the GTN parameters with the artificial neutral network. For this, we use small sliced notch tensile specimens. As it can be seen from the diagram, we use flat versions instead of the commonly used cylindrical versions because of the limited material we had. Therefore, we could save material with this method, and we wanted to show that even in case of flat specimens, we could determine GTN parameters. For this, we made 90 different simulations where we used the LH sampling method approach to randomly generate points in a defined domain. And here can be seen in the table what were the parameter ranges we used. It was based on the literature. And finally, we applied these simulation results into artificial neutral network, and we were able to generate the parameters with these simulations. And to validate the GTN parameters, we made 1T CT specimens, also made the simulations with them. And as it can be seen that results are quite in good agreement with how we determine the GTN parameters. Thereafter, so we would have the simulations with unloadings too. We made this version 2. This way we were able to analyze the data based on the ASTM E1800-2020 standard. Here the tests were done with around 40% unloadings, but when we analyzed the data, we used the recommendations stated in the standard. So here in the table, we can see the track extension and the G integral values which were determined from the standard in case of the test and also in case of the simulation. The simulation is a little bit under determined the results, but they are quite good agreement in our opinion. But to make it a little bit faster, because these were 3D simulations, we wanted to use the VCCT simulation method, where we made some changes. Basically, the first version of VCCT is energy-based. We have to have the energy value, which is based on the fracture toughness and the crack foot propagate. We changed this method, and the idea was is not to use the energy values, but for the driving force to use the critical failure values determined the GTN method. So the two methods was combined together. This way the crack could propagate as the mesh opens up, and all of the J integral to be calculated continuously during the simulation. Also, in this case, we made two simulations, one without unloading. Here we can determine the J integral directly from the simulation, and the second one with unloading. So the same way it could be generated, the J integral like previously with the standard. Thereafter, we compared these results with the test, and they were quite good agreement. There are two different initial crack lengths, as can be seen, but in both cases, the simulations and the testing results were going together. And to summarize our results, I would like to say a few words about what were the fracture toughness values we obtained. In the first three cases, we used the evaluation of the standard. It can be seen that they are quite in good agreement. In the fourth case, where there was only the simulation without unloading, the fracture toughness was very close to the tested values. The difference was only 2.4%, and because there is an uncertainty in the determination of the fracture toughness, it is a well acceptable value. So to summarize our results, we made article neutral network to use the GTM parameters generated from them. The parameters were validated with CT specimens. Thereafter, we compared them with the testing results where we used unloadings. And finally, the VCCT model was updated with the GTM method, and they were combined so it could be analyzed without the fracture toughness result, how the crack would be propagating. This method is less time consuming, and it estimates well the crack propagation and the J integral values, because the batch open up with the propagation, and also it continuously can calculate this way the J integral. We think that this method could be applied later for large-scale specimens, large-scale components, and also small-scale miniaturized specimens. And thank you very much for your attention. And also I would like to say thanks for the FracTesus project, because this is a preliminary calculations done for this, because here the miniaturized specimens are the topic. MSc Mark mentat. MSc Mark. Oh, I forgot. Una palla.
Excuse me, Mr. Scabritz. I see your screen. Could you close the sharing, please? I can't hear you. Sorry, but I can't see. I can't hear you.
Алло, слышно?
Okay, now I hear you. Please, I'm trying to system a problem that we have with the sharing of the monitor this morning for the afternoon. Could you close your sharing?
Do you see my
Yes,
экran?
I see your screen. Could you close the sharing? It's the bottom in the bottom in the lower part of the monitor in the middle. It's the green button.
Do you see my screen?
Yes, I see your screen.
I can to begin.
Could you close your sharing, please? It's the button, the green button.
Niente, lo risolviamo dopo.
Can I speak? Do you hear me? Hello? Do you hear me? Do you hear me? Slide number 2 shows a system of ordinary differential equation, the 3 continuity equation 1 and the 3 equilibrium equations 2. Slide 3 represents the equation of elasticity 3 and 4 and the dissonation. Slide 4, model of mechanical corrosion. It is assumed that on the inner and outer surface of the shell, the dependence of corrosion on stresses is expressed by the formulas 5 and 6. Here, constant AEN, MEN, AX, MXB are constant determined experimentally. T is the time, sigma is the equivalent stress. H in Hx measured from the median surface, they are the change in the half thickness on the shell. We emphasize that H in and Hx are shell thicknesses that are destroyed as a result of corrosion from the internal and external surface respectively. The thickness of the shell at each time will be determined by the formula 7. It is assumed that at the initial moment of time, the shell is under the action of specified static loads, for example, internal working pressure. Next comes the corrosion process defined by formulas 5, 7. The maximum stresses are calculated. The resource of the structure is estimated. The solution of nonlinear boundary value problems in a spatial variable is carried out by the method of multiple shooting. To discretize equation 5, 6 in time, the error method is used. Slide 5. Example. A hemisphere of radius r conjugate for a cylindrical of radius r is considered as shown in figure 1. At the initial moment of time, the structure is loaded with internal pressure. The graph of maximum stresses at the initial moment is shown as a dotted line. Then the corrosion process begins until at some point in the structure, the thickness decreases to half of the original one. The distribution of maximum stresses is given by solid line. All stresses are attributed to the yield stress. In Fig 2, all shell stress, membrane, flexural, longitudinal, and transverse are constructed. Figure 3 shows the thickness at the initial time and at the final time. Calculations were carried out at various radii of sphere and cylinder, including with toroidal adapter to ensure the smoothness of connection. But I can tell everything in 10 minutes. Thank you very much.
Professor Neimark, are you there?
Yes, I'm here.
Hello, I want to present myself. I'm Chiara Bertolin.
I'm very glad to
From
see you.
NTNU. Nice to meet you. And I
Nice
will
to meet
be
you.
the co-chairman of the session.
Yes, thank you very much. May I have the following proposal? Since due to this session, we have at least 3 talks with my colleagues.
Yes.
May I ask you to assist to present these talks?
Absolutely, absolutely. But you prefer that we try to manage everything from here, and if you have questions, you can write to me on the chat the question, or you want, because my fear is that we are unable to hear you, you know, because we are using the microphone from the computer, and it's not connected with the Zoom.
Are you hearing me in the good well?
Sorry?
Are you hearing me in the good well?
Yes, but I am able to hear you because I am close to the computer. Unfortunately, the person that are here, that are attending the session, are not able to hear you.
Okay, okay, okay.
So, but you can write to me the question, and if you have anything to say, I can say this on your behalf.
I'm sorry, the voice is not good. Maybe it's a problem with the internet, but we have not good communication with you.
Because yes, it's a bit difficult for the audience to hear you. This is the problem.
Okay, that doesn't matter. If it will be convenient for audience, if all talks will be presented by you, it's nice way also.
But in any case, can you confirm that your colleagues are here in presence or they will be online?
Since we have 20 minutes up to the start, I will call to my colleagues and will justify concerning the talks, because yesterday it wasn't any problem with that. Please.
No, but we can now. I need to speak with Francesco Iacoviano to see how can we manage if you are online. I mean, listen to you.
I'm sorry. Could you speak into microphone, because from time to time it's not so good.
Yes. So I want to understand if your colleagues that are so practically, I think you are the first presenter, or the first presentation of the session is correct. Is that led on?
Let me please just 1-2 minutes. I will call by phone because today it's a holiday in Russia. As a consequence, all our participants from my lab, they are distributed at the flat or something in other places. I shall call and will inform you immediately.
Okay, perfect. Thank you. Thank you.
Олег Борисович, если вы меня хотите позвонить, то я здесь. У вас звук выключен, не слышно, что вы сказали.
Миш, спасибо. А как у нас насчет Димы?
Насчет Димы я не знаю. Надо позвонить ему. И Анна Игнатова тоже после меня должна выступать.
Анна Игнатова звонила мне, и у нее там проблемы с электричеством, но будем надеяться, что все будет окей. Хорошо. Ладно, поскольку нас слышат, поэтому мы отключимся пока.
Le presentazioni, così vedo che abbiamo Sì, certo. Allora dopo facciamo, alla fine della sessione. Ok? Perfetto, grazie. E finisce alle 16:30.
Sì, sì.
Ok? No. Ah, questo. Friday. You need to. What is? It's already. Yes. Is there someone? Please do now. No, because we don't have all the presentation in the computer. We are an asset here. No?
Professor Bertolin,
Yes.
according to my news, at least two first talk from our team
Yes.
in line now, and I hope that the third will be also arranged in the good well.
Can you repeat? Can you repeat? Because sorry, we are.
Two first talks by Dmitry Ledon and Mikhail Bannikov. It's okay with both these talks. And the third by Anna Ignatova. I hope also because she has some problem with internet, but I think it could be solved.
Okay.
Hi, everyone.
Hello. Yes. Hello, Dimitri.
Hello. I see you hear me.
Yes.
Okay.
So you will give, so you are not here, of course, in Rome, so you will give your speech remotely, is correct?
Okay.
Yes.
Yes. So you confirm that you will participate remotely. The problem is that we are trying now to connect the audio to the room because at the moment we have some issue. Eventually, what we can do is to postpone your presentation at the end of the session if we have some trouble to solve here in Rome.
Okay. Dmitry, you understand that if the organizer will have some problems, your presentation will be at the end.
Exactly, because we are trying to manage now this issue, but I don't know if we are able to do it in time. We are just 10 minutes before the beginning of the session. Okay. Thank you.
Дим, у них какие-то проблемы с интернетом, возможно, есть. И если только они их не исправят быстро, то ваша презентация будет, как я полагаю, и всех остальных, которые дистанционно в конце.
Так, а все же работает вроде. Я даже демонстрацию запускал.
Ну вот, но все равно мы тут еще следуем их.
Ну ладно,
их
понятно.
правилам.
Не
Хорошо.
принципиально.
Будем надеяться, что все сложится у них.
Professor, trying to do a test for the audio. Hello, Professor
Neimer? I hear you, but the quality is not good. Could we speak to the microphone?
Okay, so we can do that.
Yes.
Se funziona.
Ma in realtà questo è tutto ciò che abbiamo detto, così, qualche parte adesso. Sono messo là dentro, però. Sono in rimonta.
E se io cambio qualcosa qua?
Aspetta che ti metto in viva voce.
Se io cambio l'uscita audio?
Ragazzi, ok, grazie. Professor Neimark, can you speak because we need someone?
Yes, yes. Victoria, good day. Yes, I am speaking, and the quality of my voice is good or not? Because yours, it's not too good.
Unfortunately, in the room.
Quality is your sound is good, Oleg Borisovich.
Yes, my sound is good, but our Italian colleagues, it's not so good. For you also?
Yes, for me also.
The sound level is going up and down.
Okay. Okay.
Adesso però puoi fare di nuovo?
Victoria,
can you speak, Professor Neimark?
Yes, probably it's the problem from the Italian side, because me and my colleagues, they hear all of us in the good way.
Provato con la spagnola non si sente più. Se io metto questo non si sente più. No, ma è acceso. Funziona.
According to my notice, if you will speak along your right shoulder, the voice is much better.
Partiamo col microfono.
È tutto...
No, ma pensi sta con una barra e mettiamo il microfono sempre questo.
Okay, so I can explain the plan. Now, Professor Neimark, we will start as describing in the program. So it means that the presentation of your group, the presentation of Dimitri Ledon will be the first, okay? And I will use a microphone to try to increase the volume so that you can listen in the room.
Okay.
It's okay? Perfect.
Okay.
Quelli che stanno qua.
Okay.
Сейчас через 2 минуты начнется.
Okay. Okay.
Con le stesse
Quindi
perché loro sono il Bluetooth, capito? I microfoni sono in Bluetooth e stanno funzionando. Prova ad attaccare il Bluetooth del computer. Perché non sta andando alle casse l'audio, però questi in Bluetooth funzionano sulle casse.
Ah, okay. Yeah.
Sì, 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 chiaro, chiaro.
Good afternoon to everyone. Welcome to the third section of the 27th International Conference on Fracture and Structural Integrity, IGF27. I want to introduce myself. I'm Chiara Bertolin, professor at the Norwegian University of Science and Technology in Norway, and I will be the co-chairman of this section together with Professor Ole Steinmark, that can present himself. Please, Professor Steinmark.
Yes, good day, our colleagues. I'm very glad to participate in this conference. And since we have some technical problem, and may I ask Professor Bertolin to assist in the presentation, at least our team. Okay, thank you very much.
Thank you. So in total, today we have 12 presentations. I want just to remember to the speakers that they have 10 minutes, including the question. So the first presentation is from Dimitri Ledon, and the title is Mathematical Modeling of the Behavior of Metals and Alloys under Shockwave Loading, and the presentation will be provided remotely.
So I can start?
Yes, please.
Okay, good afternoon, dear colleagues. My name is Dimitri Ledon, and I am pleased to present you my report. Laser shock painting is one of the promised methods of surface treatment of materials for the purpose of hardening. This method makes it possible to practically get rid of the effect of heating of the near surface layers, which is very important for materials which a unique structure due to the absence of recrystallization processes that level out the previous thermomechanical treatment. The shock wave actions initiated by short duration laser radiation of the order of nanoseconds is accompanied by structural phase transaction and change in the surface topography. This procedure allows obtaining unique physical and mechanical characteristics in narrow areas of the material, which increases the strength and structures and their resistance to fatigue failure. An undesirable effect that can occur during shock wave loading using a laser is spall fracture. This phenomenon can occur at a certain rate of laser power and structure size. The aim of this work is a numerical study of loading regimes using a laser. The numerical study corresponds to experimental scheme, which is present in the slide. Experimental studies were carried out in this article. The components are shown in the figure. Number 1, detectable equipment for fixing the specimen. Number 2, specimen. Number 3, laminar flow of water. Number 4, aluminum foil glued to the specimen. Number 5, laser impact zone. The problem was solved numerically in the axisymmetric formulation. The finite element method was used for the solution. Laser loading was simulated by setting a pressure pulse in the impact zone. The pressure pulse has a triangular shape. The pulse duration is 50 nanoseconds. 3 different pulse amplitudes are considered: 1, 10, and 50 GPAs. And 3 different barriers thickness are considered: 1, 0.3, and 0.1 millimeter. The complete system of differential equations for describing of the behavior of deformation and fracture of materials is as follows. It consists of the equation of motion, number 1, the equation of continuity, number 2, the kinematic relation, number 3, the constitutive relation, number 5, the kinetic equations for internal variables, number 7, 8, and 9, and the head equation, number 12. The destination of the parameters are present on the slide. The simulated options are present in the table. Only in one case there are no signs of spall fracture. It is marked in the light green color. In 5 cases, signs of spall fracture are observed, but spall does not occur. They are marked in green and blue color. The absence of spall in this situation is related to the geometry of problem, namely with the fact that the radius of the zone of influence is much less than the radius of the target. In the 2 cases considered, spall fracture occurs, and in one of the options the target is punched. The calculation for a pressure amplitude of 10 GPAs and barrier thickness of 1 millimeter is shown on this slide. The pressure distribution field is shown in the figure. It can be seen that signs of spall fracture are observed inside the specimen. However, macroscopically, it remains intact. A similar phenomenon is observed in the experiment. The image will be shown later. The calculation for pressure amplitude of 10 GPAs and barrier thickness 0.1 millimeter is shown on this slide. In this case, spall fracture occurs. 2 characteristic types of loaded specimens are shown in this slide. The results were obtained by the authors of this article. In one case, signs of spall fracture are visible, left one. In the other case, spall fracture is absent, right one. The velocity profiles of the free surface in the calculation on the left and in the experiment on the right are shown in the figure. Qualitative conformity is observed. To obtain a quantitative agreement, it is necessary to know the loading pulse in the experiment. At the moment, it has not been measured in the experiments performed. This is one of the possible ways to develop the work. And conclusions. Loading regimes that lead or do not lead to spall fracture during laser shock peening are qualitatively determined. A number of situations observed in experiments are qualitatively described. Thank you for your attention.
Thank you very much. Any question from the audience? So if not, I have a curiosity. I would like to know in real world which type of application you may have of this mathematical model?
Sorry, it's very bad sound.
In real world, which type of application of this mathematical model and you will provide?
No sound. Maybe you should write in the chat.
Yeah, I will do it. 1 second.
Professor Bertolin, the quality of sound it's not good, and maybe we could lose the time concerning question. At least audience could ask Dmitry by chat. Okay, maybe we could go to another presentation.
Thank you very much.
And Professor Bertolin, I think that the quality of my voice also will be not so good. Maybe you will announce the next presentation.
So the next presenter is Professor Liviu Marsavina with a talk titled "The Notch Effect on Additive Manufactured Polymers."
Okay, good afternoon. First of all, I would like to congratulate the organizers, the IGF group, Francesco and Filippo, particularly because 2 years ago in 2021, it was my first conference in presence after COVID in Turin, the IGF conference in Turin. There were only few people and I was the only one from abroad at that time. Now there are many people coming from even from other continents to this conference. Okay, so the title of my presentation is The Notch Effect on Additive Manufacturing Polymers. So, it's not shared? Sorry. Can you see the presentation online? It's okay? Okay. So a short summary of my presentation. We use the fused deposition modeling to print some specimens in order to investigate the notch and size effect. We did the tensile and fracture toughness static test, and then we try to apply the theory of critical distance in order to investigate the notch effect. I will not stay too much on the fused deposition modeling. It's a now very often used additive manufacturing technique due to its advantages, because became very low cost, but has advantages that it could produce very complex shape of the components. But on the other side, we have some problems with the integrity and durability of such components. Also, it is very important to understand the influence of the manufacturing parameters on the mechanical properties of such structures. And on particular, it is very important because we use to print and to design very complex shapes, we need to take into account the notch effect for this and the size effect. So very shortly, so we have a polymeric filament which is forced to go through an extruder, then it's arrive in a heater block, it's melted, and then through a nozzle is deposited to a plate plate of the machine. There are many applications and there are many studies on the mechanical properties of this. However, there are not so many studies on fracture toughness of these materials. There is probably one of the first paper is a group of Mountain University on Leoben. Professor Pinter is here. So they investigate the fracture toughness and fatty crack propagation for PLA materials using single edge notch bend specimen and compact tension specimens, and the values were around 5 to 6 megapascal square meters. Also, there are some studies on ABS and PLA reinforced with carbon fibers to determine the mode 1 and mode 2 fracture toughness. And there is an attempt done by Professor Susmel in UK. He used the equivalent homogenization material with theory of critical distance and for PLA, and having the ultimate tensile strength and the fracture toughness of PLA, he estimated a critical distance of 4.8 millimeter, and this was applied after that for several geometries of notched and cracked specimens. So what we did, we use polyethylene tetraplat glycol. We have here the parameters for printing. We use a Prusa printer. We use 100% fill. The specimens were all manufactured on the plane, so on the plane of the desk of the printer, and we use a rectilinear plus minus 45 degrees for the filling the forms. First tests were tensile strength, static tensile strength test. These were done in our trick testing machine. We use a clip-on extensometer for determining the Young modulus. We did all our tests at room temperature and with a loading speed of 2 millimeters per minute, and we use dog-borne specimens. So the value for this PET material was the value of the ultimate tensile strength was around 41 megapascals. Then we determined the fracture toughness. We use 6 single edge notch bend specimens with the same, let's say, room temperature and loading speed. We use the standard for fracture toughness determination of plastic materials because there are no standards specific for additive manufacturing materials, and we get 5 megapascal square meter the value of the fracture toughness. So with these values, we try to estimate the critical distance using the point method as was defined by Professor Taylor using an asymptotic matching. And, our specimens were 3 types of specimens, V-notch, and 2 specimens with rounded notch of 0.8 millimeter and 2.2 millimeter, the notch radius. We use 3-point band, symmetric 3-point band test, and we did the experiment in order to investigate also the size effect on different size specimens. So we use semicircular band specimens with 10, 20, 30, and 40 millimeters. We use a ratio of 0.5 between notch length and radius, and all the specimens were with the same thickness of 6 millimeters. We perform a linear elastic fracture analysis in order to get the distribution of the maximum principal stress. And with this distribution, we determine at critical length over 2, we determine the maximum principal stress. And with this value, we predict the load which should be applied to break the specimen, taking into account the ultimate tensile strength of the material. So some of the results. So we have here the effect of crack length. So we have different lengths of the crack, and the ratio between crack and R radius is here between 0.25 to 0.55. What we can see that our predicted values are in the range of plus minus 15% up to crack length of 0.5. Bigger cracks, so the predictions are far from the experimental values that we get. On the same time, we want to look on the ligament side. So use as a parameter the ligament size divided by the critical length, and we see here that the TCD is valid when the length is double of the critical distance. Below this value, so the prediction quite far from the experimental value. We also the theory of critical distance to other or to different manufacturing parameters. So we change the orientation, in-time orientation of the specimen, 0 for the previous result and 45 degrees. And we use two different filaments, color of the filaments, white filament and burgundy filament. And we can see that the predictions are quite well. We use the same value for the that was determined on the white specimens for the fracture toughness and for the ultimate tensile strength. So probably so the predictions could be improved is if we use or we try to determine tensile strength and the fracture toughness for each type of, let's say, set of material filament and for each set of the manufacturing parameters. So to conclude, so we investigate the notch effect on PET specimens obtained via FDM. We use semicircular band specimens loaded in 3-point band symmetric load. We determine the ultimate tensile strength, the fracture toughness, and we got a value of 4.78 millimeters, the value of the critical distance. Theory of critical distance looks to be valid for crack lengths up to half of the radius, and for ligament higher, 2 times higher than the critical size. So I need to acknowledge the project, the East European Twinning on Structural Integrity, the project that financed this research. And finally, I would like to invite you, some of you already submit a paper, so we have the final conference of this project, which will be in beginning of March, and from 16th of February, Timișoara is European Capital of Culture. So I invite all of you, probably for this conference or maybe with other occasions, through 2023, we are the European. So we have also the results on PLA. Yeah, we did. Yeah, for PLA. Yes. We investigate the size effect on both. The notch effect, we didn't have time to do it in PLA.
Professor Bertolin, may I ask? A very short question. Alec Naimark, co-chairman of this session. May I ask you concerning theory of critical distance? Since the characteristic distance, according to theory of critical distance, is still a questionable problem. Is it true or not? My impression that critical distance means that is characteristic size of the cohesive zone when the dota crack at the crack tip may be originated. Is it my correct impressions?
it could be considered like this, but this is not a material particularly characteristic, it's a structure characteristic. For metal, the critical distance is related to the grain sizes. For foams, for example, it's related to the geometry of the number of cells. So could be probably for plastics related to the cohesive zone.
Is it the question? I think there is a deep mechanical aspect, because the competition between stress intensity factor and characteristic stress that could be related to the critical distance is not clarified totally. Why? Because as a background for stress intensity factor, it's a self-similar solution after Irwin. But for critical distance, this kind of self-similar solution is not established up to now. It's my conclusion. I think we need we have critical situation with the time. Yes, we could go to the following presenters. Thank you very much.
Yeah, but I will present. So I don't know if I can. You can see online the presentation. No. Oh. So it's okay online. Okay. So thank you, Chiara. So I need to recuperate some time. So so this paper is a cooperation with some colleagues from University of Limoges in France. They are specialists in ceramics, and we try to determine the structure properties for some composite materials doped with some ceramic kaolin particles. So basically, we have a materials presentation, the process of elaboration. We use the Brazilian disc specimens in order to do mixed mode fracture toughness. I will present a little bit the experiments and the evaluation of the fracture criteria. So basically, nowadays, due to circular economy and we want to decrease the volume of plastic materials, and to be environmentally friendly. So in polymeric materials, there are added different types of particles. In our case, kaolin. The main application of this are electric insulators, which are used for transporting the energy. So we have a polymer resin, which is an unsaturated polymer resin, which has good electrical insulation properties, low viscosity, and excellent adhesion and low shrinkage. And these are mixed with ceramic materials like kaolin, in this case with some particles having an average diameter of 92 micrometers. So the process consists in mixing the two components with some methyl ketone peroxide and ethanol, then pouring in an aluminum cylindrical mold, which was placed on a vibrating table, then photopolymerization, which was occurred at room temperature, and what we consider the full photopolymerization after 3 days. And then preparation of the specimen, cutting the specimen, the Brazilian disc specimen in a CLC milling, then with a water jet cutting the notch. So we use classical Brazilian disc solution, where we have two, let's say, main parameter, which is the crack angle and the crack length. Our disc has a diameter of 24 millimeters, and the crack length was 11 millimeters. We perform, prior to do the test, some finite element analysis to determine the non-dimensional stress intensity factor for different angles between applying the load and the crack orientation. And we found that at around 23.1 degrees, we have pure mode 2. And between pure mode 1 and pure mode 2, we choose several crack orientations in order to do the test in mixed mode. Our tests were performed at room temperature in our testing machine, considering the two extreme 0 degrees and 23 degrees for mode 1, mode 2, and other 3 crack orientation, 10 degrees, 15 and 20. We consider 2 proportion of fillers, so 0 without fillers, 7.5% volume fraction and 15% volume fraction kaolin fillers. And we use the classical fracture criteria of Erdogan 6, maximum tensile stress, equivalent stress intensity factor of Ricard, and strain energy density criteria of criterion of SIG. And we try to express our data side by side with these theoretical predictions of the fracture. We got quite good agreement with the Ricard criterion. Point out here that the Ricard criterion is the only one which takes into account also the fracture toughness in mode 2 through this, let's say, alpha parameter, which is the ratio between mode 1 and mode 2 fracture toughness. And it looks that trigger the curve in order to have good predictions, at least at the end of the interval, pure mode 1 and pure mode 2. 0% filler, 75% filler, and finally 15% filler. Here, data are more scattered, but what we observed in the previous test done in tensile, in Limoges, they also observed that at 15% filler and more, 20%, the results became worse. Probably the adhesion and the incorporating of the filler is not anymore uniform, and the results are not so good. What we can see here, the mode 1 and mode 2 fracture toughness increase with the increasing the filler proportion up to 15%. But on the other side, the ratio between mode 2 and mode 1 fracture toughness is decreasing from around 1.5 to 1.1. I mentioned we observe similar tendency for the static tensile test and for some Sharpie test. So that's all. Thank you very much. Yeah. We have tensile on more proportion, even 0, 5, 15 proportion, but we didn't do this test for. Yeah. They produce the powder and then the specimens. Thank you, Chiara.
No, it's not. We are okay. So Sergei, okay. Are you there? You are able. Lo vedi, Francesco? Ah, Guia.
Yes, yes, I'm here. Okay.
So can you share your screen? Is the green button? Okay, perfect. Yes, you can start.
Okay.
Yes, you can start with the presentation mode. So please.
Okay. Hello, everyone. My name is Gouya Anas from Faculty of Science and Technology, Mohammedia, Morocco. And today I talk about the determination of optimal design parameters on the thermomechanical coupling behavior of strands. As a plan, I will begin my interviews with motivation materials and geometric model of strands. After that, we will say the Taguchi design as a plan of exploration characterization results. And I will finish with a conclusion. Whereof is a type of multiple layer space, called structure and consists of a central state and several other strands. Is suitable of structures with large curvature because of its low weight, height, carrying capacity, and stability during its several lives. It is widely used in various engineering structures, especially in long span space structures, such as tensile structures. We have selected a geometrical model of 1970, whereof there indicates the number of strands in the rope with a known rotation structure, considering that all the strands have the same length. Some diameter and some concentration. Using ANSYS software explicit finished element, the geometric model, the 3D model of the wear rope is established in CATIA and imported into ANSYS workbench. The wear is the strands are made of the same material and have a concentration of 0.3. A solid segment with a circular outline is allotted to each wear. This program specifies the material property generates in finished element mesh, applied loop, defined contact, and solved and obtained necessary output data. We choose the parameters that have the biggest influence, the pitch and diameter, as well as the viewing models, based on the orthogonal table, a combination of mixed level with 27 three level and three variable. The L27 orthogonal network is subjected to a pedagogy analysis in order to optimize the failure stress, with the assumption that bigger is better. The ideal combination of input parameters is found be taken into account the maximum point in the plot for different parameters on the optimal series. Our output from the primary effect plot of the signal variation. The following plotted using Minitab ANOVA. The signal variation analysis considers how to characterize performance in is measures, namely height is better and lower is better. The signal operation used in this study is based on failure stress data, with grade being better. We are selected the optimal parameter of 200 for young models, 0.2 in fraction, and 25 degrees as and here we have the variance and contribution of each factor on the response of the variables. The ANOVA has ability to give information on certain statistical parameters, such as the sum squares variance. The table gives a summary of the values of these parameters for each factor and from different equations have been written by other as a significant effect on the breaking stress forward up, followed by fraction factor 2, which has a relative effect with the temperature factor 3, has a very small influence. The effect of characterization such as material type, temperature, and friction on the mechanical behavior of the cable can be determined by combining the design of experimental DOA and the measures are found using the pedagogy design of experiments with an like shapes orthogonal network. The effect of optimal circumstance on the failure stress was investigated. Three factors were varied on their level. The failure stress was used as the basis of the confirmatory signal noise test. The pedagogy approach used in this study aims to increase the ability to provide information on some statistical parameters such as sum of square contribution, variance, and if variation ration equal 10.450. And thank you for your attention.
Thank you very much, Mr. Dr. Guya Anas. So
Yes, ma'am. I'm sorry?
So the next speaker is that is going. The title of the contribution is Nonlinear Asymmetric Formation of Shells of Complex Geometry Subjected to Mechanochemical Corrosion Under Pressure. I ask you to stop sharing your screen. Dr.
Okay.
Anas. Please, can you exit from your presentation mode and stop sharing so that we can progress with the section? Thank you. Sergey, you can share the screen now. Sergey, are you able to hear me? Can you share the screen, please? Sergey, if you are unable to share the screen, we need to move on because we are in delay.
Yes, Professor Bertolin, may I help you? Sergey, please see on the screen дополнительно, там есть 3 точки. Вот надо на них надавить, и тогда вы увидите информацию, как поделиться презентацией. Вы слышите меня? Professor Bertolin, I am sorry, but I tried to speak in Russian. Maybe it's
no. I agree, Professor Naiman. If you have problem, we can just postpone the presentation of Sergey at the end of the section.
I think it's cool. Сергей, как вы считаете, значит, коль скоро задержка, может быть, ваш доклад сместить в конец заседания? Вы слышите меня? Professor Bertolin, I think that will be better probably.
Okay, perfect. Okay.
This presentation.
So,
okay.
The next speaker is Mikhail Banikov. Okay. Perfect. Mikhail Banikov is so we are able to see your presentation. You need to go in the presentation mode. Okay, you can start with the presentation mode. The talk is titled Damage Failure Transition Staging in Carbon Fiber Composite Material Under Quasi-Static and Cyclic Loading with Acoustic and Digital Image Correlation Analysis.
Да, я сейчас слушал, там народ потом включилось, вдруг заработало где-то через полтора.
You have a button on the bottom right. Okay, but we can see.
Ну, выключил, ну и что? Алло? Не, конференция это слышна, потому что я уже не выключал.
Sergey, I'm sorry, it's Naimark speaking. Now it's another presentation. Please switch off your microphone. Отключите, пожалуйста, Сергей, свой микрофон.
Олег Борисович, меня-то слышно?
Вас слышно, да.
Да, ну все хорошо, то почему-то мне не отвечает. Окей. А когда я делаю презентацию в полный экран, ее тоже видно? Вот сейчас.
Сейчас видно, но не в полный экран.
Почему? А у меня в полный экран. Почему оно так
Ну,
не
тогда
делается?
рассказывайте. Все равно презентацию видно.
Okay. Sorry for delay. My name is Mikhail Banikov. I'm from Russia, Institute of Continuous Media Mechanics of Ural Branch in Perm. And let me please introduce the presentation of our lab. Thank you very much for the opportunity to make it. And I will start. So the first, what about I want to tell, it's an experiment which was provided by Professor Naimek and his group in 2004 by plate of polymethyl methacrylate. And the scheme you can see in this slide. This plate was deformed by different speed. And you can see that on picture C and D, the different morphology of crack tip. You can see that in C it's like normal, like glide, and in D we can see that a lot of areas of daughter cracks, branching mode. And when there are investigate the phase analysis in you can see it in E and F picture. This we can see that in the first state it's one attractor like shape oval. And if we in branching time, we can see the two attractors. That means that there are two different types of distribution of two types of laws which can propagate the crack. The aim of our work is investigation of duality of critically damaged failure transition caused by two intermediate self-similar singular solution for stress field at the crack tip, and the blow-up damage localization kinetic is used for the interpretation of two parameters fracture criteria. The presence of two self-similar solution provides a variety of crack advance depending on the load intensity of the notch type. And in our work, we investigate in composites. The first step was with unidirectional composite materials. We studied under quasi-static and cyclic loading in the block loading mode with a gradual increase in amplitude. Realization of experimental program analyzing the acoustic emission. You can see gauge here. And with digital image coloration analysis. The system is here in blue one. And the acoustic emission phase pattern in the stretched composite samples revealed the presence of two attractors corresponding to self-similar solution, which are responsible for two mechanisms of damage to failure transition related to parameters fracture criteria. And here you can see the typical energy distribution of acoustic emission events. In A and B, it's A quasi-static tests, and B it's fatigue tests. You can see that in acoustic emission, we cannot divide any two different parameters, but we can plate gradient of energy about energy, and we can make two clusters in fatigue analysis, the red one and blue one, which produced two different phenomena. Okay, we can observe two clusters associated to attractors. Here you can see the strain distribution according to DSC. A and B, it's stress strain. It's a stress strain. You can see that it's different time in different time A, B, C. It's low before the fracture, and D, it's 1 second to fracture. You can see that here in 0.8 should be fracture in that place. And first diagram of deformation critical point was analyzed in that slide. And we can observe two clusters can be associated with two attractors corresponding to a singular solution with a stress intensity factor and non-singular solution associated with T stresses. At the same time, for quasi-static loading, the division into such cluster is not so obvious. It's looking so very closely, and for fatigue loading is far away from that another. And the next step is trying to make a multifractional spectrum analysis, and you can see that for composites under condition of uniaxial quasi-static cyclic loading, for the experiment of composite of cluster 1 is bell-shaped dependencies, and the spectrum of cluster 2 degenerates into a point which characterizes that these clusters goes to monofractal properties. For the experiment of cyclic loading and the unidirectional composite, both spectra are multifractal. In this case, the spectrum of cluster 2 has a large weight. These results confirm the corrections of the decision to perform differential processing of clustering data in multifractal analysis algorithm. And the next step is analysis of composites. It was woven layered composites with a straight concentrator in the form of a hole in the center. The quasi-static and cycling tests were also carried out. And frequency was 10 Hz. And here you can see quasi-static and fatigue tests. There was very similar. Here you can see distribution of deformation, and we can see the points close to the concentrator, which are big deformation. And in that point was made analysis and build the phase diagrams. This clusterization, cluster analysis. And we can divide that there are two different laws of two different laws. And analysis for phase portraits in the coordinates deformation straight rate reflects the temporal dynamics of the development of damage during the entire loading process and the influence of two attractors corresponding to the predominant influence of stress concentration and regions of phase states large deformation. And next stage of our research was microtomography of loaded material. We cut some probes. You can see in the left side, it's first one, it's not deformed probe. Two, it's close to the concentrator. You can see this was video, and the third one it's far away from concentrator, and we made analysis, and it's very difficult to divide the damage which was in the material during the manufacturing. Like this, you can see from right side it's voids, and damage which caused by deformation. But our colleague Anna Ignatova, she will make a presentation after me, and she will talk about it very good. So it's all. It's my conclusion. You can see it. It's that slide. I will not stop it. Very big. Thank you for your attention. And if you have any question, I will be glad to answer you. Thank you very much.
Thank you very much. Please write it in the chat.
Oh, I'm sorry, I don't hear you.
Yes, we have problem of communications.
I'm sorry, it's very bad sign.
Yeah.
So, can you please print your question in the chat?
Yes, moment someone from the audience wants to print it in the chat, they have to do it. We go to the next presentation by Anna Ignatova, and the talk is titled Method of Comparative Evaluation of Integral Macrostructure Characteristics of Carbon Composite Material under Static and Cyclic Loading according to spectrotomography data. So Anna, please share your screen. Anna, please, if you're listening to her, can you share your screen now?
Anna, are you here or not? Because Anna had some technical problems.
See, Anna, unfortunately, I marked on the screen. So this point, we can just very quickly return back to the presentation of the day. If it was please. Sergey, are you able to listen to us, to hear us? Sergey, please show you. We need to progress with the section. Quindi siamo arrivati a 2000. Possiamo ok. Yes, so I think we can progress with the presentation in presence. The next speaker is Abdullah Al Ibrahim, and the talk is titled Casing Wear Mechanism under Combined Rotation and Translation.
Thank you very much. Good afternoon. My name is Abdullah Ibrahim, and today, I am in the beginning mechanical engineering student from King Fahd University of Petroleum and Metals. Today, I'm going to present the casing wear mechanisms under combined rotation and translation. Okay, our objective is to study the casing wear under the rotation and translation and compare the effect under rotation only, and investigate the different type of wear mechanism developed under different parameters and determine the dominant wear mechanism. So before we start, we take our prior work. Beats 1986 discovered the main mechanism present in casing wear. Zag 2016 found that adhesive wear and abrasive wear for two dominant categories of wear mechanisms and the rotation speed and contact load. Usman 2022 results show increasing the RPM results in absence of adhesive wear. So in the introduction, as we know, as the drilling process, it has to be in an inclined way. So our issue is when we have a contact between the casing and the tool joint, and this contact will cause wear for the casing of the well. So in these two types that we are going to study it and have different parameters and see the test. For our test, we have took a lathe machine and modified the lathe machine by inserting two stepper motors with a coupled gearbox to control the contact load and the sliding motion, as we can see here. And we have inserted also a tool joint from the field, okay? And we have a casing which has been cut by 60 degrees and installed on a casing support and holder on a dynamometer so we can calculate all of the forces. In this figure, you can see our machine. This is the figure has been taken after testing directly, okay? And for our experiment parameters, we have three types of casing material, which is P110 and L80 and SM2535. And for the contact load, we have used two contact load, which is 1000 Newton and 1400 Newton. And we use a penetration rate of 0 and 2.5 millimeters per second and a rotation speed of 115 and a lubricant oil-based. Okay, for the hardness, for the P110, we have obtained the hardness by using a hardness machine to find it. And here you can see the result. And here we have the tested sample. As I mentioned before, that the samples has been, we tested the sample of the casing. For the three materials, we can see here how is the samples affected by the wear and how it's been affected in all of the three samples. And for this to measure the wear mechanisms, we have used the SEM and the digital microscope. So for our results, the estimated wear volume for different parameters, we have tested 12 samples, okay, with the different with 3 different grades and 2 contact load for each grade, and with penetration rate and without a penetration rate. And we have obtained the estimated volume, which will be explained in more detail with my colleague, Saud. And to better show of the estimated wear volume, we can see here this graph. It's going to show you the wear volume, where we found the SM2535 has the highest wear volume comparing to the 3 others. And all of the other P110 and L80 has lower. And here the blue one has 1000 Newton, and the brown, the gray is 1400. Here, when we add the penetration rate, we'll see the difference, how it's changed from before. We have the SM still the highest, but L80 has increased, and all of them, they have higher wear volume. So we can see here the L80 and SM has to get closer to each other, okay, while P110 just increased, just not like them. Okay, for the microscope image, okay, we can see here the SM image of sample 1 with the following parameters, which is 115 RPM in oil-based and 1400 Newton, and the material is P110. We can see here, before adding the penetration rate, this figure is oriented 90 degree, okay? So we can see here, we have the abrasive wear, it can be shown here, okay? Comparing with when we add the penetration rate, we can see that the adhesive has increased and have a deep groove. Okay, the adhesive here, we found it in many locations in the sample, but after adding the penetration rate, there is no sign of adhesive. And the solid particles are present, and the solid particles are from the lubricants. So we go here for digital microscope image for the sample 39 with the following parameters: 115 RPM in oil base and 1,400 Newton, and the material is SM2535. We can find here, we found the delamination, and there is an abrasive wear on all of the sample. This is without an penetration rate. When we add the penetration rate, there is a new something that has been found. Everything looks similar, just not the same. We found here we have a perpendicular abrasive wear, which is explained by the sliding motion, because it's having it this way, so it has effect on the casing also. So it's two direction effects on it. So that's what has been observed. Okay, for the observations, okay, we took the materials which has tested by 1,400 Newton, and we have put a scale from 0 to 3, just to what have we observed. For the S1, which is the material P110, we see here in the beginning we didn't saw a lot of abrasive wear. No, it was less, but the adhesive was high. After we add the penetration rate, the adhesive disappeared. We didn't find any adhesive, and the abrasive has increased, and the solid particles also increased. In S19, the sample, we have saw the abrasive in both, where we don't have a penetration rate and when we have a penetration rate, okay, and the adhesive had decreases. And there is something that has observed also the delamination. For sample 37, we see that it has a different behavior, and everything it has a different behavior. So we can see here the adhesive has disappeared, but also the abrasive has decreases, and this is something we noticed. Okay, in conclusion, under the combined sliding and rotation, the penetration, the presence of adhesive and delamination wear mechanism will decrease also, and the dominant wear mechanism, which has been observed, is the abrasive wear for all of the samples. The P110 has the highest wear resistor compared to L80 and SM2535, and it has not shown any delamination wear in all of the sample, and this is something that we observed also. And under the combined sliding and rotation, L80 and SM25 have close wear volume. And we have assumed this happened before because there's floating of the material that happened during the testing. Since the sample has small width comparing to the reality, so this could be a factor. And thank you for your attention. And now, if anybody has a question. So yes, what we are focusing on now is to find the best material that can be used, and the well, since the well is hard to be drilled, and then it took a lot of money will cost, so it's better to select the best material that will stay with you. So now what we are observing, which in the beginning we do the research on only a rotation, then we add a sliding and a rotation, yes, and then we will add an impact. And after the impact, we will get the final conclusion of our research. Yes, thank you. Okay, thank you very much.
That is America Califano, and the title of the talk is Mechanical Behavior of CIAN or D laser joint.
Thank you, Chiara, for the introduction. Good afternoon to everyone. I'm America Califano from the University of Padua. And today I'm presenting some very preliminary investigations about the mechanical behavior of TI6AL4V laser welded single lap joints. First of all, which is the motivation behind this work? We all know that laser welding technique has superior characteristics if compared to traditional welding techniques. As a matter of fact, it allows to have reduced distortions, reduced dimensions of the heat affected zone, a high precision, and even high speeds. For this reason, laser welding technique is very appealing for the sectors of aerospace and aeronautics, especially when there's the need to join subcomponents made of titanium-based alloys. However, if on one hand, laser welding technique allows to reach very high levels of precision, on the other hand, it has a high cost. That's why there's the need to deepen the knowledge about the mechanical behavior of joints made with this kind of technique. And especially it is fundamental to understand the link that there is between the welding parameters and the mechanical behavior of joints. In this work, the case studies are single lap joints made of TI6AL4V alloy. Here you can see a schematization of a single lap joint that has been obtained by joining two plates that have a thickness of 3 millimeters, and the overlapping region has a length of 30 millimeters. And here you can see even a schematization of the welding bead. Different single lap joints have been obtained, and in particular different classes of single lap joints that are here identified with the letters going from A to F. And in particular, each class is characterized by a given turn of welding parameters that are laser power, laser speed, and laser focus. Laser power is always equal to 3 kilowatts, while the laser speed goes from 30 to 40 millimeters per second. In particular, class A and D, B and E, C and F share the same speed, that is 30, 35, 40 millimeters per second respectively. While concerning the laser focus, the first three classes share the same laser focus, that is of 0 millimeters, so it's superficial laser focus, while the other three share -3 millimeter laser focus. So we are talking about a negative defocused laser beam. In particular, we had two joints for each class, so 12 joints, and from each joint, 7 specimens were obtained by cutting the joints transversely respect to the welding bead. So in total, we had 14 specimens for each class, but in this case, only 6 specimens, 1 for each class, have been considered for the experimental tests. So the joints are identified as A1, A2, B1, B2, while the specimens considered in this case are identified as 1A1, 1B1, and so on. So the nomenclature 1A1 means that the specimen is the number 1 from the joint A1. Here you can see a schematization of a specimen on which 2 strain gauges were glued, the strain gauge E1 and E2. E1 was glued on the same face as the welding bead, while E2 was glued on the opposite face. And here you can see even a picture of an actual specimen equipped with the 2 strain gauges. While here on the right, you can see the experimental setup that belongs to the machine design laboratory of the University of Salerno. And the tensile tests were carried out using an MTS inside with a load cell of 30 kilonewtons. Well, we all know that single lap joints, when are subjected to tensile tests, tend to bend in the central area, so in correspondence of the overlapping area, where in this case the 2 strain gauges are glued. So this means that in these areas, the strains are mainly compressive. Here you can see schematization of a deformed joint specimen, where here you can see a picture of an actual specimen mounted inside the testing machine just before failure. So you can see that here there's the deformation of the overlapping area. In this plot, you can see a load strain, well, 2 load strain curves. for the specimen 1C1. So these are the two curves that have been collected through the strain gauges. And please note that these are compressive strains on the x-axis. So you have positive values, but they are compressive strains actually. And here you can see that the two curves are quite in agreement to each other. But if we take a look at the curves collected thanks to the two strain gauges for the 6 specimens, we can see that concerning E1, that is a strain gauge that has been glued on the same face as the welding bead, the 6 curves are in agreement with each other, while the curves collected through E2 are not. And this is due to the fact that mainly due to the different welding parameters, different welding penetration lengths have been obtained. And so as E2 is glued on the face that is opposite to the welding bead, the strains collected on this face are influenced by the welding penetration length. And according to this, so according to different welding penetration length, you can also have a different width D. And as a matter of fact, here on the right, you can see some pictures of the fracture surfaces. Unfortunately, the pictures are not high quality, but it is possible to assess under a qualitative point of view that if we consider, for example, the first 3 specimens or the last 3, as the laser speed increases, this width is decreasing. So the higher the speed, the thinner is this area. So this means that the specimen is weaker. As a matter of fact, this behavior can be seen even in the load displacement curves that are reported here. So you can see here the first 3 curves for the first 3 specimens, and you can see how with increasing the laser speed, the maximum load to failure decreases, and the same happens for the other 3 specimens. So in conclusion, I just showed you some very preliminary investigations about the mechanical behavior of TI6AL4V laser welding single lap joints. We up to now have tested just 6 specimens under tensile tests. And these specimens have been obtained with different welding parameters that are laser power, laser speed, and laser focus. Both load strain and load displacement curves have shown that there is a clear dependence between the welding parameters and the mechanical behavior of joints. And in particular, the strongest specimen is the one that has been obtained with a superficial laser focus and the lowest speed possible. Near future investigations will first of all deal with the metallographic analysis of the fracture surfaces in order to assess under a quantitative point of view the characteristics of the fracture surfaces, and so to link these characteristics to the welding parameters. And then the other virgin specimens will be subjected to fatigue testing. And finally, even finite element simulations will be carried out for investigating further scenarios. With this, I finish, and really thank you for your kind attention.
Thank you. Is there any correctly?
Yes, yes, to understand the kind of fracture and to link the characteristics of the fracture surfaces to the welding parameters, so both the dimensions and the kind of defects, because we think that during the welding phase, some defects, like for example porosity, yes. So that's why there are different maximum load to failure. Thank you.
No. Yuri Shah. Dr. Yuri Sharkev, please, are you able to hear me? Hello?
Yes, I am ready.
Hello, so please share your screen.
1 moment.
So in the meantime, I present Dr. Sharkev that will give us remotely a talk titled Features of the Fracture of the Alloy Ti45WVT percentage MB in ultrafine grain state at gigacycle fatigue. So please just put the presentation mode and then you can start, okay? You can start.
Yes, thank you. At first, I would like to thank organizing committee and chairman for invitation to take part in this conference. Very interesting conference. My report is devoted to future of the fracture of the alloys titanium niobium in ultrafine grain state in at gigacycle fatigue. Report are presented from me, Anna Yaroshenko, and Aykol Meranbekova from Institute of Transphysics and Material Science, Tomsk, Russia. In our work, we tried to decide two problems. The first problem is in what way we could improve the mechanical properties of titanium niobium alloy for medical application. And second problem, in what way we test our titanium niobium alloy samples in gigacycle regime during short time interval. For example, 1, 2, 3 days. This slide, you can see periodic table, and I mark it with red circle, bioinert metals at first, titanium, zirconium, and niobium, and maybe hafnium and tantalum. These metals, bioinert metals, have oxide passive films on the surface. In this reason, these metals are bioinert metals. Moreover, titanium, zirconium, and niobium alloys are used as bioinert materials for medical application. In our lab, we have dealt with different bioinert metals and alloys that used as materials for implants. At first, bioinert metals and alloys as titanium, for example, grade 1, 2, 3, 4, and titanium niobium alloys, for example, titanium 40-45 weight % niobium, zirconium niobium alloy, for example, zirconium and 1 weight % niobium. Moreover, we have dealt with resolved metals and alloys. For example, magnesium alloys, we have dealt with a very interesting alloy, magnesium 1% calcium. I'm sorry. Titanium alloy of next composition, titanium and 45 weight % niobium, is a very excellent bioinert alloys for implants. They have some advantages. They are bioinertness and biocompatibility, corrosion resistance, low elastic modulus. But this alloy has disadvantages and insufficient mechanical strength. The formation of nanostructured or ultrafine grain states in metals and alloys with various methods of severe plastic deformation make it possible to obtain bulk materials with a certain microstructure and significantly higher mechanical properties. For example, a yield strength, strength limit, hardness, micro hardness, endurance limits, cycle durability, and so on. The titanium alloy of this composition has elastic modulus in the interval 50 or 60 gigapascal. The alloys of this composition are used in medical application as materials for medical implants. The yield strength of the alloy is a normal coarse grain state is approximately 400 megapascal. This value is insufficient for implants. To improve the mechanical properties of the alloy, the severe plastic deformation are used for the significant refinement of grain structure. We use the ABC pressing methods with followed multipass rolling for ultrafine grain titanium alloys billets. You can see this scheme of this method consists of first stage ABC pressing, free ABC pressing, and maybe we use the press mold for ABC pressing. And the second stage, we used multiply rolling and groove rods at room temperature. ABC pressing included of 1 or 3 pressing steps at constant temperature. When the passing from one pressing to another, the temperature of sample was being decreased gradually by 50 degrees in the interval from 500 to 400 degrees by Celsius. After every pressing, the sample's billet was rotated about longitude axis at 90 degrees perpendicular to previous pressing axis. The application of press mold generates space limit deformation condition included effective grain refinement and minimum steps. In this slide, you can see the microstructure of coarse grained titanium alloy state and in ultrafine grain state, bottom image. The microstructure of the samples was analyzed using transmission electron microscopy. The size of structural elements were measured in TEM dark field images. The rolling during the second stage molds the ultrafine grain state homogeneously by volume, with the average size of the structure elements equated to 0.28 micrometers. The alloy billets with this microstructure have low ductility under tension, not exciting 2–3%. The annealing at the temperature of approximately 350 degrees increases the plasticity up to 5 or 6% while preserving the ultrafine grain state. Thus, we use this method of severe plastic deformation, and this method allows us to generate bar or rods with very good mechanical properties. In this slide, you can see mechanical properties for coarse grain state and ultrafine grain state. Everybody can see that ultrafine grain state has very good mechanical properties. Yield strength is equal to 600 megapascal. Ultimate strength is equal to 100 megapascal. Plasticity 5 or 6%. Micro-hardness 3000 megapascal. In this one, elasticity modulus in ultrafine grain state is compared with elasticity modulus in coarse grain state. It is equal 55-60 gigapascal. This problem connected with the cyclic test in a gigacycle regime. The surface life of the implants is at least 15 years and more. I multiply approximately 100 steps 1 minute at 60 minutes at 24 hours and 365 days and 15 years. You can see it's equal to 1 gigacycle, gigacycle. In this reason, according to mechanical requirements, implants under cycle loading must behave working life at least 10 in 9-degree cycles. We need to use special machine for testing our samples during short time. Is this reason we use installation for testing in mode of gigacycle fatigue. This is resonant type testing machine Shimadze USV 2000 Japan. Loading frequency is 20 kilohertz. This machine is located in team of Professor Oleg Naimark.
Doctor,
Next slide, you can see the data of gigacycle test results in for these titanium niobium alloy samples. You can see dependence of number of cycles to failure on the stress amplitude for titanium niobium samples. 1, coarse grain samples. 2, ultrafine grain samples.
Dr. Sharkev, please, can you go to the conclusion because you are out of the
Okay, I finished. Okay. The samples in coarse grain state we failed after 10-7 cycles at the loading amplitude of 230 megapascal. At the same time, samples of the ultrafine grain state were not failed after 10-7 cycles at of 300 megapascal. You can see microstructure of titanium niobium alloy in coarse grain state and in ultra-fine grain state. Finally, my conclusion, in contrast to samples of alloys with a coarse grain structure in which dislocation network and cells are formed after gigacycle test, in samples in ultra-fine grain states, the nature of the microstructure practically does not change during testing, but a high density of dislocation was formed. Its presence is due to the fact the formed ultra-fine grain has the maximum size for the formation intergranular dislocation structure, while the grain boundaries play a significant role in the annihilation of dislocation during gigacycle test. And second, the titanium niobium alloys of this composition in ultrafine grained state demonstrates a high fatigue properties under gigacycle loading. The ultrafine grain structure of the titanium niobium alloy is stable under gigacycle loading and provided working life up to 9 and more with high fatigue strengths. Also, this presentation thank the scientific group of Professor Oleg Naimark and our colleague from our institute for participation in the implementation of scientific research and discussion results. In this image, you can see dental implants that were developed in my lab. Thank you.
Thank you very much. So unfortunately, we don't have time for the question, and so we need to move to the next speaker.
Okay, thank you.
Introduce Dr. Saud Al-Sagir with a talk in present.
Good afternoon, everyone. I would like to introduce myself. My name is Saud Al-Sagir from King Fahd University of Petroleum and Minerals. And my presentation title is Casing Wear Volume and Factor Under Rotation and Sliding Motion. Mechanical wear occurs between the tool joint and the casing in oil and gas wells. And therefore, the wear factor should be measured. And it is very important parameter to assess the well integrity. Therefore, the objective of this study to investigate the effect of the rotation and sliding motion on the casing wear volume and factor for three different types of steels, and study the effect of the side load on the wear factor. In Breer work, only in 2060, conducted an experimental study and found that as we increase the rotational speed and the side load, the wear factor will increase. And B110 steel was the least sensitive to wear. And the Uthman 2022 provided an experimental study and found as we decrease the rotational speed and we increase the side load, the wear factor will increase. And in our experiment, we are going to study the effect of both rotational and combined rotational and sliding motion. An experimental procedure to simulate the drilling operation in oil and gas wells. We have modified a lathe machine where we have removed the cross feed and the transfer feed hand wells and we use servo motors coupled with a gearbox. And also we have used a program closed loop system to maintain a constant side loads. And we have designed a casing holder to fit any type of casing size. In addition to that, a circulation pump compact with the lathe machine was used to create an lubricant environment. And we have mount a strong magnet at the bottom of the fluid reservoir to absorb any flakes or contamination from the metal. For the measurement, this is a real picture from our experimental setup. We have used in situ displacement indicator to measure the wear depth. And this in situ displacement measure was calibrated before with previous experiment with 2D and 3D optical profilometers, and the error percent was less than 10%. To measure the side load, we have used dynamometer, and we have inserted the thermocouple on the casing surface to measure the temperature during the test. Once we have received the sample, which are real field samples, we have determined the composition of the B110 L80 SM2535 composition using optical emission spectrometry, and the hardness of the three casings and the drill pipe joint measured using universal hardness testing machine. The experimental parameters are rotational speed of 150 RPM, sliding speed of 2.5 millimeter or penetration rate, side loads of 1000 Newton and 1400 Newton, and the environment was oil-based lubricant. In result, this is the elemental composition of the three casing steels. We can observe that SM2535 has the least carbon composition, while B110 has the most. And we can also observe that SM2535 has high composition of chromium, nickel, and molybdenum. And the material hardness are shown in the right table. As we can observe that the drill pipe has the highest hardness, and this is the reason why the wear occur on the surface of the casing. If the inner radius of the casing and the outer radius of the casing is known, we can measure the wear volume using the equation number 1, where we can measure the crescent shape volume. In addition to that, equation 2 shows how we measure the wear factor, which is a common formula used to measure the wear casing, which is the wear volume removed divided over the sliding distance multiplied by the side loads. And this is the output result. The left figure shows the wear volume of the three casing steels B110, L80, SM2535 under only rotational speed of 150 RPM and two varying loads, 1000 Newton and 1400 Newton. We can observe that for all the three type steel, as we increase the side load, the wear volume will increase also. The right figure shows the wear volume for the three casing steels under combined motion, sliding and rotational speed, and the sliding was 2.5 millimeters per second. Also in this case, we can observe that as we increase the side loads, the wear volume also will increase. In the wear factor measurement, the left figure shows the wear factor for the three casing steel under rotational speed motion only and two varying loads. We can observe that B110 and L80 has less wear factor than SM25. And we can also observe that as we increase the side load, the wear factor will also increase. But what is interesting, after we add the rotational, after we apply the sliding motion, I can say almost the wear factor for the three casing steels are comparable. And to understand the sliding speed affecting the wear factor, these three figures are shown for B110, L80, SM2535. The blue column represents the rotational motion only, while the orange column represents both the combined of the rotational and sliding motion. we can observe that B110 and L80 behave similarly when we apply the sliding motion of 2.5 millimeter per second. The wear factor increased by a factor of almost 200, while SM2535 has slight effect, where the wear factor increased by almost a 4. These are some of the experimental samples: B110, L80, SM2535. It showed the Criskin shape and the worn surface. And the worn surface was analyzed with my colleague previously. In conclusion, it was found that as we increase the side load for all the 3 types of casing steels, the wear volume will increase also. And it was found also that B110 and L80, the combined motion has most effect on them. And in general, the combined motion of sliding and rotation result in much higher wear factor for all of the 3 types of casing. And this is possible explanation because now we have a friction on tangential to the casing and axial to the casing. In addition to that, we have a thin lubricant film. It might be affected by the sliding motion, and there was a turbulence. And this is the reason why the wear factor increases. Thank you for listening, and now back to the same question. Yes, for previous experiment, we were trying to use water-based lubricant, but we didn't perform the experiment because the temperature increased very high. So we are using lubricant, oil-based lubricant. Currently, we are using the oil-based lubricant, but now we are focusing to perform with impact. We are trying to use the impact. And in addition to that, we are trying to vary the rotational speed because in our experiment, we just used 150 RPM. We are trying to vary the rotational speed in the future experiments.
Okay. Okay. This is the pointer. Okay. Okay.
Okay, thank you, Chiara. Good afternoon to everybody. My name is Claudio Ruggieri. I will talk about the compression pre-cracking technique to evaluate the fatigue crack threshold. And I will try to be super fast. Okay, so let's see. This, okay. This is the motivation. Let's keep going to the motivation investigation. So as we is a very important parameter for design criteria. It's very relevant in practical applications, particularly when we have small cracks or cracks that defects that cannot be detected in the structure. And in this work, our primary motivation was from the recently discovered oil reservoirs in the Brazilian coast. This is the South. Not going to the details of this. But these reservoirs in very deep water, and makes things worse. They are underneath the pre-salt layer. So the thing from engineering, especially from the there's some technological challenges, high stress strains, the impact of these on defect assessment, high pressure, particularly sour conditions, especially high content CO2, carbon dioxide. It's a very corrosive stuff. And because of this, most of the pipelines, submarine risers, all the infrastructure, oil company is using pipes internally lined with corrosion resistant alloy, which in our case is high nickel Inconel 625 alloy. Okay, we have two types. Well, again, we don't have time. You can ask me, but we have mechanically lined pipes and clad lined pipes. For the mechanically we still have to weld to fabricate the girth weld, and the root weld overlay. Okay, and this is a very quick region because the so-called triple point, we have a combination of the inner layer, the base plate material, we usually say API 6X65, X70, and the welder. So there are many cracks, so it's a very critical region. And determining the fatigue design and the fatigue threshold is very important. So we went ahead and then we tried to investigate an alternative test protocol to get more reliable and not so conservative threshold values. Okay, the standard procedure, you don't have time, so I'll just go over it, is the ASTM E647. Okay, that is an ISO standard, which I don't remember the name, sorry, but the standard is 647, which is the so-called load shedding procedure. So you reduce decay intensity factor until the crack doesn't grow anymore. Okay. The problem with this is that this region, especially for the formable materials, structural materials, okay, some plasticity at the crack tip, and this will induce crack closure by plasticity. And we want to get rid of the crack closure, any crack closure effects. So an alternative of at least mitigating the influence of crack closure is applying a compression pre-cracking. So we start the test by a compression pre-cracking. There are a number of procedures. The most relevant procedures they were introduced by Gene Newman in the US about 10 years ago. Is the compression. So we control the test by constant amplitude. It's very tricky. It's very difficult. And simpler way, we work with the compression pre-cracking load reduction. So essentially we apply compression pre-cracking. In other words, we grow the crack by compression, and then after we are satisfied with the cracking, and then we grow the crack, or we determine the threshold by using a load reduction technique, which is very similar to the load shedding procedure of ASTM. Okay. This is an experimental program, so we did a lot of testing. This is a standard stainless steel. No big deal here. So it's 250 megapascal with stress, high hardening. We choose this test before doing the weld, or testing the welding, because we are doing the welding. But the welding is very tricky, many parameters. So we actually start with the procedure by using testing a homogeneous material. So the 316 steel is kind of similar to Inconel 625, not the same, but similar. Okay. And then we applied two specimen geometry. A standard contact behaves very well, and CB specimen, 3-point bend specimen. And why the 3-point bend specimen? Because a pipe, it's very difficult to extract a compact specimen because we have to align the specimen with the longitudinal pipe direction. Okay, and this is the more or less the scheme of the bent specimen in the girth weld. Okay, but again, because of these specimens are small, because of the thickness of the pipe, we kind of had problems with the standard bent specimen. So in this work, we also got a non-standard bent specimen where we increase the span. You can see here the specimen with a larger span. It behaves much better, as I'll show you later. Okay, and for the compression, the compression, we apply the compression load metallic blocks. And for bent specimen, we use a 4-point bending scheme because it has zero shear stress, constant bending, much easier to apply the compression scheme. And don't have to go into details, but determine more precisely the pre-compression load, because we don't want a very large pre-compression load, otherwise we just mess with the test. So evaluate this using a finite element analysis, 3D finite element, using the cyclic stress-strain curve. Okay, not showing here because we don't have time, but we have more details. And then very quickly on the results. Okay, this is the CT specimen, expected behavior. The CT behaves very well for those who have the CT specimen. Okay, and even using the load reduction, see here the again behaves very well and does shift the curves to the left as we would like to, and altogether. So we have the load procedure 647. The load reduction, you can see here the threshold is smaller as we kind of got rid of the closure effect. We didn't get a very good result with yet. We abandoned during the test because it's very tricky and it's very, very time consuming. Okay, don't do that unless you need it for very specific reasons. And then the bent specimen. You can see here that the standard does not behave well. Very jagged curve, a lot of scatter. That's because we get a lot of plasticity in this. Okay. When we S of W8, you can see here that their behavior. Okay. This is the 647 standard. And this is the load reduction. That you just get a lower threshold as we intended. And those are the results when put together. You can see here the CT, okay, using 47 standard. And then you can see here that it's very close. The span helps a lot with the test for the load reduction compression preparation. Okay, so I'm done. Just to finalize, so the threshold displays geometry dependence, okay, especially for the bent specimen with standard geometry. And then when limitations exist on material availability, which is the case for pipeline, we recommend using a non-standard specimen with increased span. And at least for this material in this work, we did not see much improvement using the compression pre-cracking technique. Okay, it does improve a little, but we believe it's a lot of work for little gain. So just stick with the standard procedure. And so I think speed on right. Okay. Okay. So I think they have to get coffee. Yeah. Cycles, it's a try and error with the calibration of the finite element analysis. So actually, we need to do a try and error with some dummy, what's called dummy specimens. So we have to break specimens and measure to see if we are in the right direction. So after it's a lot of work. So as it's within threshold. I mean, every time you mess with threshold fatigue, it's a lot of work. And here's the thing. I mean, the procedures, engineering procedures for the pectoral thermal, they specify a threshold of 2 megapascal square root meter, which is very low. And one of the reasons is that there is no much reliability in determining in the lab, unless you have very specific reason. Okay, so that's it. Okay. Thank you.
Yeah, so I want to thank all the participants, the speaker, and also the person that has attended this section, both in presence and online. So I want to thank in particular, one second that I'm trying to close this. So I want to thank you very much, Professor Neimark, for co-chairing this section together with me, and all that participated online. Thank you very much.
Thank you very much, Professor Bertolin, and all audience and speakers for this nice opportunity to discuss our results.
Thank you. Now we have the coffee break. Thank you very much.
Thank you very much.
Allora, ragioniamo come sono stati Tuesday, domani è Friday, session, e non so tu dove stai, non ne ho la più pallida idea di dove stai. Parli ora? Sì, un attimo, allora carica lui. La 12ª. Questa qua è la chiavetta tua, ci sta il buco di qua. Ricordati il numero 12. Questa, scommetto. CTRL C. Andiamo di qua. CTRL V. 12. Allora, questo sta a posto. Posso chiudere la tua chiavetta, scaricarla. Tanto che questa è Windows 11, quindi funziona. Okay. Sta andando. Un attimo, oggi è giovedì, lezione 4? Lezione 4?
Prego, oh, se no posso fare io tanto. Ah. No, così ci metto pure il numeretto di... Qual è? Qual è la... Scusi, qual è la... Questa? Non questa qui. Questa qui. Sì, l'apriamo per controllo. Mi dici il numero del 5? Ma la presentazione numero 6 non si vede? Non si vede. Però vedi? Chi la fa la presentazione numero 6? Ma è? Ah, quindi non è... Ah, sì. Sì, sì, vabbè, carichiamola al volo. Qual è? Scritto questo. Un attimo che allargo questo qui. Sì, sì. Lei è il primo? Scusa. Sì, sì, si vede. Sì, che seduto e frontale perché i microfoni sono qui, altrimenti online non la sentono. Quindi non si giri a guardare lo schermo. Che posso chiudere, tanto funziona. Un attimo che si riscola.
Forse lo faccio la parola.
IGF27. Tutte e due devo copiare? Sì. Questa non la carichiamo. Allora che questa non la carichiamo. No, devi fare così a voce. Che numero è, Daniele? Invece De Maio stavo qua dentro a fare assistenza. Qualcuno per caso ha fatto le cose di là? Le mie cose di là nessuno l'ha fatte. Sì, perché nel frattempo mi ha chiamato da qui. Se no insieme a qualcuno andava a fare qualche cosa dopo gli indiani, mi ha chiamato pure Arpino mentre stavo qua. No, perché stava a fare il cocer, quindi potevo rispondere. No, perché lui è il terzo. No, l'ast è pure vista. L'ultima. Ma già che non la manda a San Dottorato un po' di tecnologia, è sempre grande cosa. Questa credo. Io la minaccio che la manda a fare il dottorato un po' di tecnologia. Io la minaccio che ce la mando, invece l'ho fatto veramente. Che l'ho fatto.
perché so com'è lì. Anche se lei parla con gli altri dottorandi e confermano. Prego. Io sto morendo di caldo in questi giorni. Domanda. Non mi ci metti a parlare. Posso tolgo quel 2, non c'entra niente. Parla frontale che almeno ti sentono là. No, no, parla frontale. Una cosa, quando, non so per quale motivo, quando va la presentazione, tipo, me lancio una a casaccio, no? La prima. Lancio la prima. Allora, quando condividi lo schermo, in realtà cosa devi fare? Devi mandare in presentazione. Però ora ci sta l'altra cosa, non la posso mandare io. Comunque, mandi in presentazione e ci sta lo screenshot, il salvaschermo della pausa. Mandi in presentazione, poi start, apri Zoom, perché se, cioè, come mandi in presentazione questo scompare la barra sotto, quindi devi premere start e così ricompare la barra, clicchi su Zoom, Zoom certe volte si mette si riduce, quindi devi andare a cercare la cosetta piccola. Per il primo sto io qua, dai. Lo apri e mandi il secondo schermo. È lui. E certo, perché è lui. E dopo cerchi là, cioè quando metti secondo schermo ti si fa un cerchietto, un contorno vestino attorno a questo schermo che sta di qua. Funziona. Io non te lo posso fare perché ci sta lui in condivisione. Allora, semplicemente devi... infatti qualcuno mi ha chiamato. Allora, tu devi prima condividere, cioè devi, scusa, devi prima mandare in pro e poi condividere. No, su Zoom tu non devi fare nulla perché gli sta lui. No, ma solo lui. Il problema, lo sai qual è? È che a ogni volta che chiudi il PowerPoint si perde il secondo schermo, quindi come esci dalla mia modalità presentazione, il secondo schermo si perde e Zoom ti dice sono uscito. Lo dice proprio lui. E quindi tu ogni volta ti fa stiller. Meglio, così ti hanno fatto le domande. Sì. Che fa? E non ti sentivano se parlavi girato di là, perché dovevi parlare guardando di qua. Non sta il coffee break? Vabbè, è semplice. Quindi non ci sta nessuno, sono tutti in presenza, perché nella sessione di prima c'erano i russi che non sono venuti, quindi io stavo qua col microfono, non so più una cosa, a reggere perché lo stavano in premore. No, perché in teoria stavo andando con l'altro, ma invece mi sembra.
Perfetto.
Thank you, Chairman, for your kind presentation. This work concerns a particular type of self-acting materials, that is, polyurethane resins filled in cementitious capsules. This kind of material has been analyzed with normal mechanical testing in the past, but now it is also analyzed by the acoustic emission techniques. And we used two particular types of polyurethane resins to fill in these capsules. The first one is Carbostop U, and the other one is Carbostop F. And the specimens that are equipped with these capsules are named PUC if we use Carbostop U resin, or PUF if we use Carbostop F resin. The PUC resin was accelerated and highly expensive, while the other one, PUF, was not accelerated and was slightly expensive. And we embedded this particular type of capsules in particular specimens that has dimensions of 40 per 40 per 160 centimeters. Then we made experiments to PUC virgin specimens, on PUF virgin specimens, and also on specimens named REF that are not embedded with this kind of capsules. Then we made comparison between the behavior under 3-point bending tests of these different specimens. And also we made some fatigue loading to understand the durability in time of this kind of self-failing material. In this picture, I have reported a PUC specimen after the collapse with the resin that spread from the capsule. On the right, I have reported the typical setup of a 3-point bending test, and the specimen is equipped by 2 acoustic emission sensors on the top of the specimen itself. To analyze the behavior of these materials by acoustic emission, we utilize a comparison between the absorbed energy under 3-point bending test and the emitted energy, that is the acoustic emission energy. The absorbed energy is the fracture energy. While during fatigue test, we employed the most important parameters in acoustic emission that are Kaiser effect, felicity ratio, and calm ratio. In this picture, I have reported the behavior in time, the loading in time, in a static three-point bending test of a PUC virgin specimen, and it is compared by a self-felled PUC specimen. We can see that we have more acoustic emission in a virgin specimen than in self-felled specimen. In the bottom, I have reported the force versus displacement in time of a virgin specimen and the fracture energy calculated time by time. At the end of the test, we have the total fracture energy absorbed by the specimen. The same we tested on a PUF specimen that is equipped with the other resin, and we have this kind of results. In synthesis, we tested 56 specimens, RF, PUC, virgin, PUF virgin, etc. And we obtained these synthetic results. We can see that the maximum peak load is reached by the REF specimens that are not equipped with the capsules. The maximum fracture energy is related to the PUC virgin specimens, while this is a very an interesting graph in which we reported the fracture energy related to the peak load. And we can see that the PUC virgin specimens and also the PUF virgin specimens are brittle, because increasing the load, we have a reduction in the fracture energy, while the RAF specimens are more ductile, because increasing the load, we have an increasing in the fracture energy. Also, this kind of behavior is related to the specimen, self-felled specimen, PUC and PUF. Okay? This is another interesting graph from my point of view, because considering constant the fracture energy, we have a different acoustic emission signals in the PUC specimen self-felled related to the PUC specimen virgin. Therefore, the PUC specimen are more tougher, because they absorb more energy and emit little energy. Okay? This is an interesting interpretation of the behavior of these two kinds of specimens. Therefore, the self-felled specimens are good, considering the behavior from a mechanical point of view. Then we made some experiments by fatigue, and we used the most important parameters by that can be detected by acoustic emission. That is the Kaiser effect, the felicity ratio, and the calm ratio. What is the felicity ratio? The felicity ratio is the ratio between the load in which we reached the acoustic emission signals and the maximum previous low in a fatigue test. While the calm ratio is the number of acoustic emission signals in the unloading branch of the repeated load related to all the acoustic emission signals in the cycle. Then, by utilizing these two parameters, we can say if the specimen is in minor damage, intermediate damage, or under EV damage. And this can be represented by this kind of diagram that is invented by Fowler, Timothy Fowler, in 1977. And we can also test the specimen by considering this kind of behaviors. This is a test in which we applied a repeated load, a cyclic load for 5,000 cycles. And we can see the program of loading, that is a force in a range between 100 Newton and 600 Newton, and this is the acoustic emission cumulative force. By applying the felicity ratio parameter, the calm ratio parameter, etc., we obtain this kind of behavior during the test. Therefore, considering the medium of these two values, we can explain that the specimen was in light condition of stress. Therefore, it do not collapse. While considering this other kind of loading program, we have a collapse after 600 cycles. By considering the calm ratio, the felicity ratio parameter, the calm ratio parameter, we say that we have a situation at the end of the test in this position. Therefore, it is demonstrated that by the acoustic emission it's possible to understand if the specimen will collapse or do not collapse. And this is a synthesis of this analysis, in which we have here the specimen that collapsed, and in this other position, the specimen that was in stable condition. It is also interesting to make a comparison between the self-healed specimen under 3-point Bendis test static, in which we have this kind of rate in acoustic emission and this kind of acoustic emission cumulative curve. And this is a specimen, a self-healed specimen, tested to fatigue, the first one, and after tested under static 3-point bending test. We can see that we have a minor, less number of acoustic emission signals at the end of the test. On the left, we have 90 acoustic emission signals. On the right, we have 60 acoustic emission signals. It is also interesting to say that we have a rapid increasing of the acoustic emission signals just when the load reach a value near to 600 newtons. That represents the Kaiser effect. But we can also say that the absorbed energy of the specimen on the left is about the same of the absorbed energy of the specimen on the right. This is the reason why the specimen do not collapse, because after or previous the fatigue loading, the fraction energy absorbed by the specimen is the same. Okay, and naturally, to have a more complete picture of this testing, we have to do other tests, but also considering the behavior analysis, but I think that are in a good position to understand if the self-healing materials. Thank you very much. Okay, thank you very much for your attention. And
Okay, thank you for your kind presentation and good afternoon to everyone. Today I'm going to show you our numerical results about the crack-induced degradation of vibration characteristics in FP-plated reinforced concrete elements. This work has been carried out with the contribution of Professors Greco, Lonetti, Luciano, and Nevone Blasi, and Doctors Pranno and De Mai. We know that in the last years, structural health monitoring is gaining more and more importance in order to avoid the risk of catastrophic failure in existing structures. In the classes of damage detection methods, vibration-based techniques are based on the concept that the damage will alter the dynamic properties of the system. And it is possible to detect the occurrence of damage phenomena by measuring the dynamic structural response. To the vibration-based methods belong the data-based and the model-based techniques. The first one are based on statistical model of the extracted from time history responses, while the second one are based on physical models of the monitored structure. We then saw the structural health monitoring procedures based on the coupling between numerical models and experimental data. Our approach has been implemented into a 2D finite element framework. And in order to take into account all the complex nonlinear phenomena such as concrete crushing, rebar yielding, and FRP debonding, we incorporated two different submodels. The first one, known as diffuse interface model, and introduced by some of the authors, is able to reproduce the crack onset and propagation in the concrete phase and FRP debonding phenomena by the insertion of cohesive elements along the boundaries of the finite element mesh and along the material interface between concrete and the reinforcement system. The second submodel, instead, called embedded truss model, is able to reproduce the interaction between concrete and steel rebars. Our numerical simulations involve a 4-point bending test performed by Amado and co-author in 2015. Preliminary, we analyzed a reinforced concrete beam without FRP system, without any reinforcement system. So we evaluate the ultimate load, and we define 9 unloading levels as a fraction of the failure load. We can see that each unloading path exhibits residual plastic deformation. And for higher damage level, for example, from L6 to L9, we can see that each curve has 2 different slopes that are related to the combined effect of the concrete plasticity and the partial contact between the crack faces, which cannot completely close to the presence of aggregates and the sliding phenomena that occurs at the concrete rebars interface. After the static analysis, a linearized eigenvalue problem has been solved by performing the analysis of small amplitude-free oscillations superimposed on the damage scenarios obtained at the last point of each unloading path in order to take into account all the complex nonlinear phenomena previously introduced. So we can see on the left of the slide the degradation of vibration frequencies for 7 selected mode shapes, and on the right we can see a comparison between the experimental envelope and our numerical model of the frequencies for the first mode shape. After the validation procedures, an FRP strengthened reinforced concrete beam has been analyzed with the same methodologies and procedures used on the control beam. We added 3 new load levels in order to capture the rebar yielding and FRP phenomena, the bonding phenomena. And we can note immediately that after the yielding phase, each curve exhibits low residual plastic deformation compared to the control beam, due to the strengthening effect provided by the FRP that influenced the global stiffening of the beam. Instead, after the yielding phase, we can see, due to the linear phenomena such as the concrete plasticity and the partial contact, we have bigger residual plastic deformation. Solving the linearized eigenvalue problem for the FRP plated beam, we can see in the slide the reduction of the normalized frequencies for 4 selected mode shapes. And we can see that each path has 3 different slopes. The first one that is related to the elastic stage, the second one that corresponds to the crack formation stage that is characterized by a fast evolution of the damage processes, and the last one that corresponds to the stabilized crack phase. And then we can see that after the yielding load, the frequencies drop with a steeper slope up to the peak load. Finally, we evaluated 2 of the most common damage indicators available in the technical literature. The first one is the modal curvature. Analyzing, for example, the modal curvature for the first mode shape, we can see that the early load levels, the change in the slope that indicate the presence of damage are in the central part of the beam. Subsequently, the effect on the FRP that is mainly provided in the bending zone limits this change, and the peaks are registered in the lateral part of the beam. However, it's important to note that the modal curvature influences the fracture process near the beam support and near the plate 10 influence the modal curvature for the high order mode shape, because we can see higher peaks in the lateral part of the beam where no really damage is present. So to overcome this issue, we need a another indicator that is not focused on a single mode shape, but that are based on the summation all over the investigated mode shapes of the absolute differences between the modal curvature obtained at the generic coordinate. And this is the curvature damage factor, because we can see in this slide that the peaks are proportional to damage and therefore to the crack length. So in conclusion, we proposed a numerical model that with a properly calibration of some parameters is able to take into account all the typical nonlinear phenomena that are induced by cycling loading conditions, that are the loading condition really present in existing structures. And in the light of the obtained results, we can conclude that our numerical model could be a useful tool for the damage detection in a reinforced concrete structure, also strengthened with FRP. Thank you for your kind attention. Yes. This one. No, we use a diffuse model of cohesive. So we use a cohesive model diffusing all the part of the beam where we expect that there are cracks. So it's a diffuse formulation of the cohesive models, and we have to use this kind of mesh also to reduce the induced effect of the mesh. And then in the interface between FRP and the concrete, we use a cohesive zone model, also introduced by the editor, named as a single interface model on a line to capture the bonding phenomena, for example. Thank you. Yes. We can see in this slide, for example, in the last part, the last picture, that we can capture the bonding phenomenon, the point C of the load deflection. Instead, the load deflection curves return to the control beam that at the bottom part. Yes, it's symmetric. No, only on the bottom part of the beam. The lamination we capture for high order mode shapes, yes. 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 Bending block, yes. The difference even in the factory processes, for our point of view, it's not yes, because we have, for example, the bonding the plate end or in the partial the bonding. Yes. Still. Thank you.
Thank you for the presentation and good afternoon, everyone. The work that I'm going to present is about the failure analysis of nanofilled ultra-high performance concrete structure. This work is co-authored with Professor Lonetti in Greco and Penna and Dr. Leonetti and Pascuzzo. In recent years, the main limitation of ordinary concrete have been overcome by using ultra-high performance fiber reinforced concrete, abbreviated as UHPFRC, due to very high compressive intensity strength, ductility, and durability. A recent study has showed that incorporating nanofillers in UHPFC structure lead to improved performance in terms of strength and fracture toughness property. Several nanofillers are used as a reinforcement, for example, carbon fibers, graphite nanoplates, carbon nanotubes. So, despite the high number of experimental investigation, a few numerical models exist in the current literature that analyze the effect of nanomaterials in UHPFC structure. So, for this reason, for reproducing graph propagation phenomena, we develop an efficient finite element modeling that combine the moving mesh technique for reproducing the geometry evolution caused by the crack advance, the international integral method to extract fracture variables at the crack front, and R curve concept to capture the ductile behavior of this structure. So, besides the spatial and material system, the moving mesh introduced a new mesh coordinate system in accord to which mesh nodes can move independently from material nodes. So the various frames are linked by propping mapping function, which are needed to express all governing equation with respect to the mesh configuration. Moving mesh adopts the Laplace regularization approach for reducing mesh element distortion. The M integral expression, starting from the J integral applied to superimposed state, formed by two admissible files, the actual one, for which stress intensity factor would evaluate, and the auxiliary one whose solution is enough. Finally, in the recurve model, the fracture resistance, expressed in terms of fracture toughness or energy, is a function of the equivalent crack extension only. Now, in this slide, show the procedure for evaluating hair curve, starting from an available experimental Lloyd curve. It consists in three different steps. Step one, performs finite element analysis for calculate load mid total deflection and stress intensity factor as a function of the relative crack depth by varying the latter in a discrete manner after assuming a constant depth increment. For each crack depth, the value of the related shape function V and K are found. The second step performs a curve fitting analysis to obtain an analytical surrogate analytical model in terms of closed form expression of V and K. The third step performs three further sub-steps using the obtain analytical expression. So at the beginning, the initial value of the shape function V and the effective elastic modulus are evaluated. After that, the relative crack depth for all points of the measured load displacement curve are evaluated. After finally, the critical stress intensity factor for all relative crack depth value are evaluated and used to derive R curve. The crack propagation mechanism is managed by an automatic algorithm. The analysis starts by defining geometry, mechanical property, boundary condition, and initial mesh configuration. During the simulation, the loads are slowly increased. For each increment, the stress intensity factor at crack front are extracted and used to evaluate crack onset condition and direction of propagation. When this condition is fulfilled, the propagation occurs. So the moving mesh advances the crack tip to simulate the propagation. During the propagation, the elements around the crack tip are distorted because of the mesh motion, and remeshing events occur exclusively when the quality of the mesh is compromised. Now, to verify the reliability of the present method, we consider two crack problems. The first is a 4-point bending test under poor mode 1 fracture condition. We consider 4 different mixtures of UHPFRC. One without non-enhancement, and the other contains 0.1, 0.2, and 0.3% graphite nanoplates. So this graph shows the error curve obtained by using a numerical procedure explained previously in terms of critical stress intensity factor as a function of the crack extension. Instead, this graph compares curve load versus deflection of midpoint of the beam predicted by the proposed method with the experimental prediction. So the results are in excellent agreement with them. In addition, this graph shows the great influence of the amount of GNP reinforcement on the overall peak load and post-peak behavior. The second example involves an asymmetric 4-point bending test under mixed mode fracture condition. We analyzed 4 different geometric configurations. The scale differs according to the distance C and C1 of the load point and the pre-crack location, both measured from the midpoint. In particular, case 1 involves fracture under poor mode 2, and the other case involve mixed mode crack propagation. The results in terms of load versus crack mounts like displacement show how the peak load increase at increasing value of mode 2 component over mode 1 component. And this can explain by increasing the crack path tortuosity, as we can see from the finally crack trajectory. Finally, here we can see the crack evolution for case 1 and case 3. So, in conclusion, a novel finite element modeling approach for the numerical simulation of crack propagation phenomena in nanofile UHPFRC structure is proposed, which combines the moving mesh technique, the international integral method, and the recurve concept. The proposed strategy has been validated through comparison with experimental data, and thus denoting that if the error curve is accurately calibrated, this strategy ensures accurate prediction. So despite extensive formulation, the moving mesh technique reduced considerably the recourse to remeshing events. And finally, the proposed procedure can be effectively employed for simulating crack propagation phenomena under poor mode 1 and mixed mode condition in nanofile UHPFRC structure. Thank you for your attention. Okay. Okay. I said during the presentation that the moving mesh introduced a new mesh coordinate system. This system has the property of moving liberally into the space according to specific condition that can be not related to the mechanism of the investigated problem. So in this setting, the moving mesh adopts a proper rezoning technique based on regularization approach, and this to guarantee the motion consistent during the propagation without excessive distortion of the mesh elements. And so this property causes a considerable reduction of remeshing events. Okay.
io forse posso questo. Thank you, Professor Vantadori, for the introduction, and good afternoon, everyone. Today I will present a numerical model to analyze reinforced concrete structures retrofitted with non-enhanced FRP systems. This work was developed with Professor Ascione from University of Salerno, Professors Greco and Lonetti, and Doctors Sgambiterra and Pranno from University of Calabria. The recent progress in nanotechnology has highlighted, motivated many researchers to employ the nanomaterials in concrete structures. However, as highlighted by several experiments, only amount of nanomaterials embedded in concrete matrix improve the compressive and tensile strength of these structures. Moreover, nano-reinforcement have been also embedded in composite materials in order to improve the bond strength, for example, between concrete and FRP layer in retrofitted concrete structures. With respect to the high number of experimental works, there are few numerical models able to take into account the presence of nanomaterials in concrete matrix or composite structures. In general, such kind of structures should be analyzed by multi-scale models in order to simulate the different mechanical behavior occurring at the nanoscale or microscale, such as the crack bridging offered by the nanotubes or the bonding between mortars and aggregates. Therefore, these models require a great computational effort, and usually macroscale models based on phenomenological type methods are preferred. Therefore, in this work, a macroscale model based on a cohesive fracture approach is proposed to analyze reinforced concrete structures retrofitted with FRP plate bonded to the concrete surface by means of nanomodified epoxy resin. The theoretical approach of the proposed model relies on a variational formulation defined over a discretized domain, whose the kinematic is enriched by interface element placed along the boundaries of the mesh. The interface behavior is governed by an intrinsic cohesive law, whose softening depends on a scalar damage variable. Now, some computational detail of the proposed model are described. In particular, the proposed model consists of three different submodels: the diffuse interface model for damage evolution in concrete phase, the embedded truss model for simulating rebars and their interaction with concrete, and a single interface model to simulate the bonding between concrete and FRP plate. The first one, as explained by my colleague Daniele Gaetano in a previous presentation, consists of zero thickness cohesive elements placed between the bulk element of the mesh to simulate crack onset and propagation. The second one models the rebars as elastoplastic truss elements and relies on a relation to describe the bond slip behavior between concrete and steel reinforcement. The third model instead relies on cohesive elements placed along the physical interface between concrete structures and the FRP system to simulate potential debonding phenomena. To take into account the reinforcing effect of nanomaterials, such cohesive elements are equipped by a trapezoidal bond slip law. In fact, as highlighted by several experiments, the incorporation of nanomaterials makes the resin more ductile, improving the shear strength and the fracture energy. The proposed model is virtually validated by performing a W shear lap test on a concrete prism with an unenhanced FRP layer. The results are in good agreement with the experiments, showing the good capability of the proposed model to predict the stronger structural response offered by the non-enhanced specimen. Moreover, we can see that the incorporation of nanomaterials in epoxy resin modify the failure modes of the specimens. In particular, the debonding of the FRP is accompanied by the detachment of the concrete substrate in the sample with nanomaterials. Then the proposed model is employed to analyze reinforced concrete structures retrofitted with non-enhanced FRP plate. The numerical results show that the nano-reinforcement does not provide a sensible improvement in the loading carrying capacity. However, an increment of about 5% of the peak load is predicted by the non-enhanced structures with respect to the beam without nanomaterials. Also, in this case, different failure modes are predicted by the proposed model. In particular, the non-enhanced beam show the concrete cover separation failure due to the higher shear strength offered by the non-enhanced FRP plate with respect to the tensile strength of concrete. An interesting result concerns the crack pattern predicted by the proposed model. In fact, the non-enhanced beam is characterized by a diffuse cracking within the concrete cover and by a reduction of the width of the main cracks with respect to the beam without nanomaterials. In conclusion, this work, an empirical model based on the cohesive crack method, has been proposed to simulate the mechanical behavior of reinforced concrete structures retrofitted with an non-enhanced FRP system. The numerical results obtained by the simulation are in good agreement with the experiments and highlight the good capability of the proposed model to simulate the rule of nanomaterials in retrofitted concrete structures. Thanks for your attention. Yes. Yes, the first step, yes. By the validation test on the concrete prism. What? By comparing the numerical results with the experiments, with the calibration. What is the same yes. Yes, the same specimen, the same test. Yes, this model is already employed in other works, and the validation of the model is made in this work. No, the softening for the cohesive element inserted between the interface between concrete and FRP, we use a trapezoidal bond slip law. And for the cohesive element inserted between the bulk element of the concrete mesh, we use exponential softening law. For the concrete, usually such kind of law is used for this test.
Thank you, Chair, for the presentation. Good afternoon to everyone. This topic is, which is still in progress, is developed in collaboration with colleagues from University of Calabria, in this case with Professor Lonetti. How can I? Sorry. Okay. So this is a brief overview of the presentation, an introduction, research goals, materials and methods, results and discussion, conclusion, and acknowledgements. In general, we use composite material in the construction field for repairing, as is here reported in this photo on the left, or as construction material. In this case, we are speaking about pultruded profile. The name came from the industrial process to produce this material is pultrusion. In this case, we have a unidirectional fibers embedded in a thermoset matrix. Within this material, in general, using thanks to the high anti-corrosive properties, these material are in general, okay, in this case the video doesn't work, but this kind of material are used especially in aggressive environments. In this video, my idea was to show you this kind of material in contact completely all their life with water. In this case, tap water. We are speaking about a cooling tower, or are used for, like in this case in Germany, to replace a previous concrete bridge with a new one in glass fiber reinforced polymer. Okay, now the video is going. All these kind of structures involving GFRP materials member are connected each other by bolted connection, adhesive connection, or a combination of these two technology. In general, we can see that the adhesive connection is the best one for this kind of material. We know from literature what about durability of fiber reinforced composite material, and we know that for a period of 9 months was experimentally demonstrated that the mechanical properties can decrease of about 10% to a maximum of 50%. But what about the adhesive that we use to repair or to build a pultruded profile? For example, in this case, we have a technical resin. One is on the left is a Cicadur 30. On the right, we have Araldite from 2 different companies. And what is reported probably here is is that the thermal properties like glass transition temperature is a function of curing the temperature. And also, obviously, the strength of the mechanical properties of the resin is a function of the time and the temperature. High curing temperature is not always possible to reach because in civil engineering, we are speaking, we can have a logistic problem. For example, for Cicadur 30, the best temperature to obtain the highest glass transition temperature is 45 degrees, which is not very easy to reach in our field. So the consequence is that TG is not always the highest possible. In civil engineering application, ambient temperature is the most common situation we have. So the goal of the research is try to increase the thermal and mechanical properties of adhesives cured at ambient temperature by adding nano additives into the binder in order to increase the glass transition temperature, or into the hardener in order to increase the strength of this material, with a particular regard to the hygrothermal durability. The first step in order to achieve this goal was to study two commercial epoxy resin as they are. The first one was Cicadur 30, and the second one was Araldita. We cured these both resins at room temperature, 23 degrees in this case. Their technical data sheet report these two glass transition temperature. We study, first of all, we study the thermal properties of two resin. Here we have results for Cicadur, and here we have results for Araldite. If we point our attention on these two graphs, is evident that the glass transition temperature for the Cicadur 30 was evaluated like 45, lower than the maximum glass transition temperature obtained, but a more elevated temperature. So that one of Araldite is 70, is quite similar to the highest possible. The curing degree of this resin, according to this room temperature curing, is 82% for Cicadur 30 and 97% for Araldite. We have performed a huge experimental program in order to evaluate the behavior of adhesive in contact with seawater and tap water. In particular, we built adhesive, quite 200 adhesive joints. Adherence was in GFRP, and the adhesive was Cicadur 30 and Araldite. We selected the temperature of 30 degrees to liquid, seawater, and tap water. The observation period was 15 months. And we evaluated the fracture energy in mode 2 by end-notch failure laboratory test. This is the absorption results relative only to the adhesive. Here we have seawater, Araldite versus Cicadur 30. Here we have resin in tap water, again Araldite versus seawater, and here we have the absorption behavior of joints, of adhesive joints. So in this case, we have adhesive plus adherence in glass fiber reinforced polymer. In order to evaluate the fracture energy in mode 2, we use a end-notch failure test. The geometry of the specimen is here reported. We use, in order to evaluate the fracture energy, and so also the air curve or cold resistance curve, the compliance beam basic method, which is the convenience of this method is that the fracture energy is a function of the initial compliance of the specimen and the equivalent, the initial crack length, instead of an equivalent crack length. We evaluated for both adhesive 3 points. We know the most common one are Pmax and Pu. At Pmax, the cracks starts to grow. At Pu, the cracks stop. From this point to this point, we evaluated the resistance curve. We evaluated also in these curves this point, which is detect the end of the linear elastic behavior. On the air curve, we can see that this refers to the Cicador 30, which is a linear elastic behavior. In fact, this racing has a brittle failure. This air curve refers to the Araldite, which show a more ductile behavior than the other adhesive testing. Parallel to this three-point load, we can evaluate the three different fracture energy. This one is the classical fracture energy, and this one, the first point, is the fracture energy at the end of the linear elastic behavior. We evaluated finally the fracture energy for an aged specimen, for aged specimen in seawater and in tap water. As is possible to see, we don't have a great decrease in terms of strength and stiffness for specimen with the Cicador 30, but we have a sensible decrease in terms of strength and terms of stiffness when we use Araldite adhesives. If we make a graph of fracture energy, fracture energy over the time, we can see that we have a reduction in terms of fracture energy of 20% for Cicador 30 and 60% for Araldite. Okay, we have evaluated in order to transform the fracture energy in interface law for design purposes. We have developed a numerical analysis evaluating parameters which influence the behavior of these joints. We have a perfect agreement between numerical and experimental results. We have translate fracture energy in interface law, finding the shear strength in the case of tap water, in the case of seawater. Now we have completed the study of state of art of these two common commercial cold curing epoxy, and now we are ready to try to modify the glass transition temperature. We have also to take into account that our standards limit the use of service temperature of about 15 degrees lower than the glass transition one. So our idea is to increase the glass transition temperature and also curing degree by using a nano additive. Thank you for your attention. Yeah.
Thank you, Professor Vantadori, for introducing me. So today I'm going to talk about this work, which is a collaboration between us from the University of Cassino, the Norwegian University NTNU, and the Research Center SIRA. So first of all, a brief introduction. The electron beam melting process, which is a process which falls part in the powder bed fusion category, starts with a metal powder which is previously atomized according to one of the several existing methods. And then after a layer by layer production cycle, we will obtain our components and a certain amount of waste powder. And in order to improve the process efficiency and to lower the production costs, it is possible to reuse this waste powder in the next manufacturing cycle. So starting with this waste powder is firstly sieved in order to eliminate any damaged particles, elongated particles, and so on. And then it is also possible to mix this sieved powder with other virgin powder. And this is mainly due in order to lower the oxygen content. And then starting with this mixed powder, another layer by layer manufacturing cycle can begin, and at the end of which we will obtain our other components, this time made with recycled powder and other waste powder. So the aim of this work is to understand the differences between these components made with recycled powder and these components made with virgin powder, and of course, differences between the powders itself. More in detail in this work, we analyzed 2 batches of titanium powder particles, grade 5. The first one is virgin powders produced with a plasma atomization process, and the second batch is a powder recycled more than 100 times. And then manufactured with these 2 batches of titanium powder particles, we have 3 samples for each batch, so a total of 6 samples. In order to carry out some microstructural analysis on the 2 batches of titanium powder particles. And then regarding the samples, we made both the microstructural and the defects, the internal defects analysis. Here there are some results from our previous work. And as can be seen, the virgin powder is characterized by a lot of these tiny particles, which are called satellites. And as can be seen, the recycled powder, after 100 cycles, is characterized by a lower number of these tiny satellites, which is good because the flowability is increased. But at the same time, a lot of damaged particles appeared, such as the elongated particles, broken particles, and so on. And in addition, also the oxygen content in recycled powder is increased. And this is detrimental for specific fields such as the aerospace field. We also analyzed the internal situation of the particles, and we also made some quantitative analysis using the ImageJ software. And we saw that the virgin powder is characterized by a higher amount of these defects. And this is due to the gas entrapped in the powders itself during the atomization process. And the recycled powders, due to the preheating inside the ADM chamber, is characterized by a lower amount of this porosity. So in this work, we analyzed regarding the powder particles, the microstructure. The virgin powders is characterized mostly by a martensitic microstructure, and this is due to the fast cooling rate during the atomization process. While regarding the recycled powder, we saw that most of them are characterized by a quartz-ended microstructure. This is due to the lower cooling rate during the production cycle. But not all the particles exhibit the same microstructure. As can be seen from these particles highlighted in green, this is most similar to the virgin one. And this means that each powder particle experienced a unique thermal history. And this is true because some particles are closer to the melt pool. Other particles are far from the melt pool. This is something interesting that we found, which is this alpha case, which is a layer rich in oxygen around the powder particles. This is visible only in the recycled powder. But this topic needs to be properly investigated because this alpha case is also characterized by a higher hardness. So we need to do some nano hardness evaluation in order to better understand this aspect. Here is the sample preparation. So we sectioned all the samples in order to analyze both the situation in the upper part and in the lower part, because we also wanted to understand if there are any differences, any influence regarding the building plate. And then we simply performed a metallographic process in order to obtain this embedded sample and to observe the defects. And then through the etching process, we also investigated the microstructure. So here the results, we saw that both the kind of samples are characterized by the typical defects, which are the typical defects of the electron beam melting process. And they are mainly due to the process parameters. The only defects which are due to the recycling process are all of these tiny porosity, which are due to the gas entrapped in the powders itself. Here a more detailed view. We also performed an image quantitative evaluation in order to see the percentage of defects. And we saw that the component made with virgin powder is characterized by a higher amount of defects. Then regarding the microstructure, we saw no particular differences between the two kinds of samples, and both in the longitudinal section and in the cross-sectional, and both in the upper part and in the lower part. The microstructure is mainly a basket wave one, which is a typical microstructure in the titanium components. But something interesting was these prior beta grains, which tend to follow the building direction. This is true for both the components, but this is true only in the center of the specimen. As can be seen here close to the edges, so in the surface, there is no specific direction for these prior beta grains. So in the conclusion, in this work, we analyzed the defects and the microstructure in both powder particles and then samples made from these powder particles. And we saw that the virgin powder is mainly characterized by a martensitic phase due to the fast cooling rate during the atomization process, while the recycled powders is mainly characterized by a quartz-ended microstructure due to the lower cooling rate. Then the recycled powders also exhibit an oxygen-rich layer, which is known as alpha case, which is also characterized by a higher hardness. Then regarding the components, we saw that both the components are characterized by the typical defects, the defects typical of the powder-bed fusion processes, which are due mainly to the process parameters. Regarding the microstructure, we saw that there was no differences between the two kind of components and in both upper part and lower part. The microstructure was basket wave, so it was mainly the same. Something interesting was this prior beta grains, which tends to follow the building direction. This was true only in the center of the specimen, while close to the edges, there was no specific direction. So thank you for your attention. Yes, so as I said before, this work is a collaboration between us from Cassino, the Norwegian University, and the Research Center, CIRA, from Capua. And this analysis were carried out by the CIRA Center from Capua, and the results will be available soon. But something which are expecting to find is a narrower distribution, size distribution, for two reasons. The first one is the sieving procedure, which tends to lead to a more homogeneous powder particles. And the second reason is the preheating inside the ABM chamber, due to the fact that the tiny particles tend to melt on the surface of larger particles. Thank you.